Okay, good evening, ladies and children, and boys and girls, and everyone else that's out there in the peanut gallery world. Today we're looking at the sun, and now we're up to light. So if anyone sees the light, let me know. Before it's too late.
Hallelujah.
Don't go to the light.
Oh, we're going then to the light. We are going to light, and we're going to use the all-important and very knowledgeable Wikipedia site. Jen's saying volume very low. Sorry, Jen, that's your volume, not mine. This Carol Ann did it. Don't go into the light.
Poltergeist.
Oh, poltergeist. Oh, okay.
And the mob is like, do it, do it. That was all. That was my contribution to the light discussion.
I wish I had Peter's other screen because I could have it as full screen. Then I could read this easier. I think that first paragraph doesn't really have a lot of relevance, but we'll just go straight to the sunlight is a portion of the electromagnetic radiation given off by the sun. In particular, infrared.
Terry, just check your output level at OBS, because remember they're hearing you through OBS, not through Zoom. You're fine in Zoom, but you might be a bit quiet in the actual YouTube stream. Just in case your audio level has got knocked down a little bit.
Checking to see. I haven't adjusted that before. That's always set at that level.
Well, so apparently you're quiet in.
But everyone else's volume as well, not just me.
Well, remember they're hearing all the rest of us through Zoom, and your volume is fine in Zoom, so it's not your microphone, but it could be your output to YouTube.
Your volumes are peaking well into the off the scale. My volume's peaking pretty well off the scale.
Well, apparently yours is about half of our volume, so you might want to just boost that up for a bit. Maybe it's going out okay, but I don't know. Maybe.
You're just somewhat quieter than Alan or myself, Terry.
Have I got an adjustment?
Yeah, you sound fine on YouTube to me. I just listened.
I don't know
where. You hear you fine on YouTube.
I don't know what I've got to adjust that.
You're fine, Terry. I can hear you okay.
Oh. That's weird. Adam says it's all okay at his end.
Mm-hmm. Yeah, I just put YouTube on the big telly there and you sounded fine.
Yeah, and I'm checking the OBS mic levels, and I'm right up at the end of the scale for output. And voice meter's not changed. It's set at the normal levels. Everything's right there. Okay. Nothing's changed from normal settings.
Mm. John Stock says you're all good as well.
Yeah, all good this end. Okay.
Oh.
What was I? On Earth, sunlight is filtered through Earth's atmosphere and is obvious as daylight when the sun is above the horizon. Yeah, okay, that's usually what happens. The direct solar radiation is not blocked by clouds. It is experienced as sunshine. A combination of bright light and radiant heat. When it is blocked by clouds or reflects off other objects, it is experienced as diffuse light. The World Meteorological Organization uses the term sunshine duration to mean the cumulative time during which an area receives direct irradiance from the sun of at least
Irradiance.
from the sun of at least 120 watts, wow, per square meter. Other sources indicate an average over the entire Earth of 164 watts per square meter over a 24-hour day. Now, are they talking about that's just direct sunlight or not diffuse sunlight? Obviously, they're talking about,
Yeah, that's direct sunlight. And of course, the problem is that the direct sunlight, assuming there is no cloud anywhere, the direct sunlight at the equator will be much higher than the direct sunlight at the pole on a solstice, because of the fact that we're on a sphere, so angle the sun makes to the surface changes with the angle that the ground is at.
well, how can it still be a 160 watt per square meter on the entire Earth in the daylight? Well, that wouldn't be even.
That's
Uh,
an average.
Well,
Click on
that's a
top of the
minimum.
citation. If you click on the number 2, it should take you to the citation.
Yeah. On the number 1, we'll take you to the citation for the. But basically, yeah, basically what it means is that to for it to be recorded as sunshine in the meteorological data, the sun, because the weather forecast often has the number of hours of sunshine, or weather reports have the number of hours of sunshine that you've had, and to be defined as having sunshine, you need to have that 120 watts per square meter arriving at the surface. If it's less than that, then it's not recorded as sunshine. Because obviously, if you have solid cloud all day, you would have the weather would be recorded as 0 hours of sunshine.
Would it be too early to start bringing up if we're talking about these watts per square meter? How that relates to using solar panels? Or is that something different again to connect the two there?
Well,
You probably want to discuss the
if
photoelectric effect before you went to solar panels.
Oh, okay. Yeah, I don't want to go.
well, it
I don't
also
want to jump around too much with things and get confused with where to go from here. That's one thing I don't want to do.
what one can say is that the 120 watts per square meter or the 164 watts per square meter gives you a maximum, or sorry, gives you a maximum amount of power that you can get out of a solar panel, because the most you can ever get out of a solar panel is the amount of energy that is falling on it in in useful solar radiation per square meter. And of course, depending on the type of solar panel it is, will depend upon how much of that energy is actually useful to the solar panel. Because the radiation from the sun, the sun has a black body radiation temperature of approximately 5,500 Kelvin, and which is basically the middle of visible light. It's kind of green lightish color, and the spread either side of it is all added together to get that 120 watts per square meter. Now, if you've got a solar panel that is heating water, that is far more reliant on the infrared end of the light spectrum to work than a photovoltaic type solar panel that is producing electricity, which works much more in the UV and blue-green end of the spectrum.
If you look in
So,
just to make Alan's explanation just a little bit easier, Terry, I've dropped a link on the internal chat that shows the difference of the light wavelengths and how they come through our atmosphere compared to outside of our atmosphere, and the different wavelengths, how they actually travel through.
That one?
Yes, that one there. So that
I
shows.
wish they wouldn't make the damn thing backwards, though.
I'm sorry, Alan. That was the quickest.
Yeah, I know. They've got the wavelengths. They've got it the wrong way round for the energy, haven't they? Because it
Yes,
should be
yes.
long wavelengths to the left, short wavelengths to the right, which works correctly with the energy.
Yeah.
And
So it's that in essence shows the difference of wavelengths. So where that peak is on the far left of the screen, that's basically our visible light, where the infrared on this particular graphical representation is the right is the infrared light that comes through, and the left would be the ultraviolet light that comes through. Now, this is all obviously in micrometers, and as you can see,
nanometers.
Nanometers. Correction, thank you. It shows that the visible light that comes through is somewhat more powerful than the infrared as it goes down that scale. And like Alan was saying, that shows the graphical representation of why using infrared to actually create hot water becomes somewhat more difficult on a purely sunny day. You get more visible light coming through. However, once that cloud cover comes in, that infrared light level isn't necessarily affected as much as the visible light that is affected.
Actually, the infrared end of it is pretty good because it doesn't get scattered so much.
Yeah,
Which is
it
why we
stays a
get red
constant.
skies at sunrise and sunset. So you tend to get far more constant, but which is great for heating water. The thing is that the photovoltaic cells, the ones that you get electricity out of, work on all the stuff at the left-hand end of the graph most efficiently. They just don't work off infrared. So you need to. It's also why they work so much better on satellites.
Yep.
That's why satellites don't need such big solar panels, because as you can see, the spike at the blue end, which is pretty efficient for a photovoltaic, is a lot bigger.
and being outside of our atmosphere, as you can see by the shaded scale then, when the blue light doesn't have to go through our atmosphere, it's somewhat more powerful.
I probably need more explanation on that graph because
Yeah.
that's not really showing me anything.
All right, so
Stuff to the left is far more energetic. Stuff to the right is less energetic. Stuff to the right will warm a thermal solar panel up very nicely, thank you. While stuff to the left is good for making electricity from.
So I'll just read the quick blurb that goes with that graph, Terry.
With the difference between the two pretty much being the yellow green line.
Yeah. So I'll just read the quick blurb that goes with it. Solar radiation is radiated electromagnetic energy from the sun. It provides light and heat from the sun and energy to photosynthesis. The radiated energy is necessary for the metabolic and environmental and the habitats. The three relevant bands of range along the solar radiation spectrum are ultraviolet, visible, and infrared. One of the light that reaches Earth's surface, infrared, makes up 49.4% while visible light provides 42.3%. The ultraviolet radiation makes up just a little over 8% of the total solar radiation. Each one of these bands have different impacts on the environment. The amount and intensity of the solar radiation that the location of the body of water receives, depending on the variety of factors. These factors include latitude, season, time of day, cloud cover, and altitude. Not all radiation emitted from the sun reaches the Earth's surface. Much of it can be absorbed, reflected, and scattered in the atmosphere. At the surface, solar energy can be absorbed directly from the sun, called direct radiation, or from the light that has been scattered and has entered the atmosphere, called indirect radiation. Most of the solar radiation that reaches the Earth is made up of visible light. Visible light and infrared light. Only small amounts of ultraviolet light reach the surface.
Which is a very, very good thing, because UV light is really bad for us.
Yes.
In big doses. Yes. Nobody likes sunburn, do they?
No. And that's the important thing to realise, that like after going in that direction away from the ultraviolet wavelength, once you've finished being in the ultraviolet, the very next one after that's X-rays. So we all know that when you're having X-rays, it's something that your dosage of that is something that you shouldn't exceed, a level per year. But fortunate for us, our atmosphere somewhat controls a lot of that from coming down to us. And it's the same with gamma rays.
Would you like a really useless piece of information that might be completely relevant to the conversation?
Yeah, go.
The distance the amount of curvature, the amount of drop in the curvature of the Earth at a distance of 1 meter is 70 nanometers, which is right on the join between UV and X-rays.
Yep.
Just throwing that out there, like it's really tiny. Spit roasted piglets. Spit roasted piglets sounds good.
So you're saying if we go over the curve of the Earth, we'll get X-rayed?
No.
Not quite. You'd
No.
have to go to actually hit X-ray. You'd have to go about 3/4 of a meter rather than a whole meter. Not very far at all. I mean, well, it's really difficult to measure that amount of curvature because you're going to have to use X-rays to do it. Because you can't actually see it. You can't actually see something that small using visible light.
We've got the bacon got out in the chat, Terry.
Yeah, I'm on it.
We all miss you, Bacon God. Right. Oops. Back.
Yay!
Right, back to Wiki. Yeah, that graph, I might have to break that graph down into individual components to understand that sort of level of explanation. Where were we up to? Watts per meter. Oh, the ultraviolet radiation in sunlight has both positive and negative health effects, as it is both a requisite of vitamin D synthesis and a mutagen. We're going to get mutated.
Yeah, so a lot of if you get struck with a whole heap of the certain bandwidths of ultraviolet radiation, it can cause your cells to mutate.
Wow.
So that's why
Yeah.
our atmosphere is so
Terry,
good.
you know how? Yeah, sorry, Peter, didn't mean to
No,
interrupt.
you're right.
Yeah, what I was saying about the energy of the photons, which is why I didn't like the graph because it's back to front in the high energy is on the left instead of on the right. The energy in ultraviolet light, there's enough energy in ultraviolet light to actually knock electrons out of atoms. And this is a bad thing because in things like DNA molecules, it it can actually it can actually damage the DNA enough that it causes mutations in the DNA.
And that's where you get your skin cancers and stuff like that from, Terry.
Exactly. That's why prolonged exposure to the sun is bad for us. I mean, we need a little bit because we do need to get the vitamin D synthesis going. But if we go too far, we then get things like skin cancers. Now, obviously, it is an issue in the UK, but it's nowhere near as big a problem for us as it is for you guys. Because I mean, I remember all I remember the sunscreen song from about 1984 ish. You know, slap your sunscreen on when you're going outside crap thing. That even managed to be a hit in the UK as a health message.
Sunlight takes about 8.3 minutes to reach Earth from the surface of the sun. A photon starting at the center of the sun, they mean the center or the center of the outside, and changing direction every
No,
time
the center of the,
it encounters a charged particle which would take between... Oh, what? I have to read that again. A photon starting at the center of the sun and changing direction every time it encounters a charged particle would take between 10,000 and 170,000 years to get to the surface.
Yeah, so if a photon was to leave the center of the the center of the sun, and every time there was a collision with another photon or another particle, another charged particle, the amount of times that it would be bouncing backwards and forwards within the sun itself would take between 10 and 170,000 years.
That's a bit hard to get your head around, that, isn't it?
It's a long time. So in essence, what they're saying, Terry, there is the sun we're seeing, the light that we're seeing now was made in essence before man was on Earth.
Okay.
Although it only takes the 8 minutes to get here, the light itself
from the surface.
Yeah, from the surface, the light itself that was produced within the sun was produced before man was even on the Earth.
Sunlight is a key.
Before modern man was on.
Yeah. Sunlight is a key factor in photosynthesis, the process used by plants and other autotrophic organisms to convert light energy normally from the sun into chemical energy that can be used to synthesize carbohydrates and to fuel the organism's activities. Now that brings it back to life starting on Earth, even with the sunlight, how it helped organisms to convert their light energy into a chemical. Okay. So out of reading all that, I think where we could go. Well, we could go down the road of the photosynthesis to use by plants and convert light energy, chemical energy that can later be used to released to fuel the organism's activities. This chemical energy is stored in carbohydrate molecules such as sugars, which are synthesized from carbon dioxide. I'd have to read more on that one.
I think if you're more interested in the actual sun, you probably want to keep scrolling down and hit the contents and get to section 1, measurement, and then composition and stuff like that. Because there's lots of the important stuff is actually further down this thing rather than what we've talked about so far.
So we're going to measurement. Oh shit, there's math here.
Of course there's math. How else are you going to measure stuff if you're not going to measure it, if you're not going to quantify it? Yeah, I'm sorry, dear boy, but we're going to measure things, we have to quantify.
Okay, researchers can measure the intensity of sunlight using a sunshine recorder, a pyranometer, or a heliometer, to calculate the amount of sunlight reaching the ground. Both the eccentricity of Earth's elliptic orbit and the attenuation by Earth's atmosphere have to be taken into account. Oh, so we have to. Okay, so Earth's elliptic orbit is. So because we're revolving around the
Yeah,
sun and all that sort of stuff.
because
Okay.
remember it's an inverse square law for how much how much of the light reaches you. So to measure the light output from the sun, you have and compare it on different days. You have to know how far away from the sun we are.
Okay. So the
Because
extraterrestrial solar luminance corrected for the elliptical orbit by using the day number of the year is given to a good approximation by. Oh shit, then we have to work all that out. I'm not going to try to work all that out.
yeah,
So
it's
basically you've got equals for days, month, dates, um, except leap years. Um, and then we've got also in this formula, because it's in modern times. Oh, I can't read that because that's further down.
Earth's perihelion, which is the closest approach, is just after the solstice. So it's about January the 3rd, and not on the solstice.
Well, we're not the same distance from the sun all the time.
No, because we're
No.
not in a circular orbit, we're in an elliptical orbit.
Ah, okay.
So the bit where we're closest, which is 3 is the sun, one is sorry, 3 is the sun, 2 is perihelion, and 1 is anhelion, is it? I can't remember the
I think it said it here, didn't it?
Aphelion.
aphelion, yeah. That would be it.
It doesn't say here.
Yeah. Well, maximum E external is on January the 3rd.
Well,
Yeah,
that's something else I'm
because
going to
that's
have to
the
look into is
closest.
the Earth's orbit to the sun and all that sort of stuff. That's a separate thing I should have looked into. In astronomy, extinction is the absorption and scattering of electromagnetic radiation by dust and gas between an emitting astronomical object and the observer. Interstellar extinction was first documented as such in 1930 by that guy. However, its effects have been noted back in 1847. Wow.
Yeah. So anyway, reading that, I can see that one of the numbers in that equation, which you've now scrolled past, so the 0.033412 is basically the ratio between the perihelion and aphelion distances in astronomical units. Oh, sorry, it's oh no.
The value of that number is determined knowing that the ratio between the perihelion squared and the aphelion squared should be approximately
Where
0.9.
Yeah, so I'm betting that 0.33412 is the square root of 0.9353838.
So there's a solar illuminance constant. Is that E something? Is equivalent to 128
Is 100
times 10 to the power of 3
times 10.
lux. Roll down to get to that.
That's the SI.
That one.
Yeah, and lux is the SI unit for illuminance.
Derived unit of luminescence measuring luminous flux per unit area. It is equal to 1 lumen per square meter. In photometry, this is used as a measure of the intensity as perceived by the human eye of light that hits or passes through a surface. It is analogous to the radiometric unit. There'll be more information there too.
Watts per square meter.
Yes, it says if the terrestrial, oh well, there's more to read there. Mouse gone. Okay. What bit was I up to? Up to here, I think, was I? Got what I was read up to. Okay, we've got the solar illuminance constant is equal to that of lux, the direct normal illuminance.
Yeah, that's how much is coming off the sun.
Corrected for the attenuating effects of the atmosphere is given by that formula, where C is the atmospheric extinction and M is the relative optical air mass. The atmospheric extinction brings the number of lux down to around 100,000 lux.
Yeah, so it reduces it from about 120 to about 100 kilolux.
By the time it hits the surface of the Earth.
By the time it hits the surface of the Earth.
Yeah. So what the sun can be is brighter. If the sun's brighter out in space, does that mean the effects of the sun is better? Like better for other usages? Like that they use the solar arrays things on the ISS and all that sort of stuff?
Well, yeah, because you've got so if we've got 120 you got
I'm wondering how they measured it. Yeah, you can
you've
you can
got
measure something on Earth, but until you went to space to confirm your measurements for how bright it is in
you've
space.
got about you've got right the the luminiferous lux on the surface of the Earth is about 83.3% of the lux at the top of the atmosphere. So you lose about, what is it, 16 and 2/3% of the light is absorbed by the atmosphere on the way down. Given that you've got 120 kilolux per square meter at the top and 100 at the bottom.
Okay. So the total amount of energy received at ground level from the sun at the zenith. At the zenith, does that mean like at the equator or something?
Well, when the sun is at its height,
At the highest, okay. Depends.
It's maximum height.
Yeah, depends on the distance to the sun, and thus on the time of year. Okay. You'll see all this sort of stuff. I think I missed a step, knowing the Earth's rotation around the sun to know how far away it is and all that sort of stuff. So, oh shit, missing a step doesn't help when you want to learn something. It is about 3.3% higher than average in January and 3.3% lower in July. See, that's not really a lot, really, is it?
Well, no,
3%.
we're not. The eccentricity isn't huge because it's not really. Because remember, you're getting we get summer in July and it's in the northern hemisphere and it's not really colder than in the you know you don't have particularly hotter summers in the southern hemisphere than we get in the northern hemisphere. So the distance to the sun isn't really particularly big. That 23 and a bit degree tilt is what really matters for getting energy onto the ground.
If that's the case, I don't think they're giving me a. Oh, that's not what I want. Does that help, that image?
It just shows you what the zenith is, i.e., when the sun's at its maximum height above the horizon. I mean, the sun is only truly at the zenith if you're on the equator,
Yeah, that's what I
and
was
it's the
saying, the
solstice,
equator, yeah.
or you're in the tropics, and it happens to be the day when the sun is directly over your head. At noon.
Okay. I keep forgetting where I'm up to. It's got here 1050 W per square meters.
What's per square meter?
So the total amount, direct and indirect, from the atmosphere. Okay.
Oh yeah, because you get about 70 watts per square meter of indirect energy coming down as well. That's assuming there aren't any clouds.
Yeah. In terms of energy, sunlight at Earth's surface is around 52 to 55% infrared, above 700 nanometers.
Yeah, that's what we just said. Lots of infrared. Half the light at the surface is infrared because infrared is not the atmosphere doesn't absorb infrared nearly as much as it absorbs the shorter wavelengths.
That's one of the reasons why we had so much of an issue when we had the hole in the ozone layer, Terry, because the ozone layer is one of the layers that actually absorbs a lot of the ultraviolet, and as we've already read, the ultraviolet is one of the the prime causes of skin cancers and stuff like that. However, because it's been blocked by our atmosphere, it's the other two spectrums, being the visible wavelength spectrum and the infrared, are the two that give the most amount of energy to the Earth.
just getting my eyes focused. I keep losing my spot.
Yeah, so
I was up to here, wasn't I?
52
Up
to
to
55. Yeah, 52 to 55% infrared. 42 to 43% in the visible, which is 700 to 400 nanometers, because we need to work in the opposite direction to the way they've got it. It's just asked backwards.
Well, that doesn't help me, does it?
Yeah, well, wavelength always has to go from longer to shorter, never from shorter to longer.
Have we got a better representation of this?
No, because at those wavelengths, talking about frequency gets really difficult.
Oh.
Because if we take what 500 nanometers, that's so, oh, hang on, I've got to find what the SI doodahs for what the SI multipliers are.
Yeah, I'm just trying to wrap my head around what. Because I know light has different wavelengths, like infrared, X-ray, and all that. And I know light can be broken up into different colours, like in a rainbow.
Oh,
So
the,
is that the part of the thing to do with infrared and X-ray, or is that something different again, where the light goes into different
the,
colours,
the,
like a rainbow?
Terry, did you just break Alan?
I don't know. I've only picked up
right,
on bits and pieces to do
the
with light
problem
over the years.
the problem is that light light in the middle at about 500 nanometers has a frequency of 6 times 10 to the 14 meters. Sorry, 6 times 10 to the 14 hertz, which is approximately 16 terahertz. Sorry, 100 is approximately 600 terahertz. That's why they tend not to use frequency and start using wavelength, because it's more convenient. It gives you more useful information at those frequency wavelengths combinations to talk about the wavelength than the frequency. But we have to remember that the long wavelengths should be on the left and the short wavelengths should be on the right of any graph that is talking about anything to do with energy from the photons, because that's the way it works. But everybody talks about the short wavelength first and then the longer one, because most people are used to dealing with talking from small numbers to big numbers. But with wavelengths, we talk about big numbers we talk about going from effectively large numbers to small numbers. And yeah, it so yes, this keeps breaking my brain because it's backwards.
Well, how about we go into the to something that makes it easier for you to explain it. If we can find a graphical representation of what you're saying, these wavelengths Like that
Well,
graphic Peter showed a minute ago, but that was back to
that
front or
graphic
something.
that graphic that Peter showed a minute ago, if you flip that along its horizontal axis, my brain would cope with it much better.
Okay. Well, we'll see if we can
Particularly because
find.
it puts the high energy on the right side of on the right hand end of the diagram.
Okay, we'll have a break for a minute, and then we'll see if we can find some sort of images that might be able to help explain some of these terms and things we've been talking about here. Okay. So, what would I type in? Just wavelength or sun's wavelength? Sun's.
Hang on, Terry. I'm now just going to go off and find.
Okay. Okay,
I'm
talk
going to
amongst
go off and
ourselves
find.
then.
Let me just go find the.
Yeah, I said that, and we'll just talk amongst ourselves for now. What are you doing, Chris? So I need to start digging the outhouse. What? I'm just reading the peanut gallery. M. Ball said they could have measured from mountaintops and calculated the difference at sea level to figure out what space was. They could have used balloons to measure before satellites. Okay. Conversations all over the place in the peanut gallery.
Sorry. Right.
Renee and me back, been cleaning house. Wife is getting ready to have surgery and she's worried about what she'll be able to do. It's all good. I've got it covered.
Yeah.
Okay.
Now there we go. Now there we go. We have long waves, small frequencies down at the bottom, and we have big frequency. We have short waves, big frequencies at the top. As you come up, you've got on the wavelength side, you've got some things of what you're looking at, and between 1,000 meters and 100 meters of wavelengths, you've got AM radio and some FM and a little bit and some FM radio. Then you come up a little bit further to 10 meters to a bit less than a meter, which is from around 40 megahertz up to around about a gigahertz. You've got your VHF TV stations, FM radio stations at around 100 megahertz, VHF TV stations above that again, and then at the top end between about 500 megahertz and 900 megahertz, you've got UHF TV. Then above that, you've got microwaves from 3 gigahertz upwards, and that's the frequencies where you have radar and Wi-Fi and Bluetooth and all of that. You come up further to and that's in the gigahertz, right? The radar is in the gigahertz to hundreds of gigahertz range. Then above that we have far, what they call far infrared, then thermal infrared, near infrared, as you get shorter from 1 millimeter down to 1 millimeter, which is 1,000 micrometers. You've got thermal IR at 100 micrometers, infrared at 10 micrometers. Then the near infrared, which is what we were talking about earlier, which is around 1,000 nanometers or 1 micrometer. You've got that small gap of visible in the 700 to 400 nanometer range. UV then runs from about 350 down to 35 nanometers, which of course includes that 1 meter distance of Earth curvature at 70 nanometers. And then, and we're then, you're getting up into the really big frequency values here, 10 to the 16 hertz, 10 to the 17 hertz. Then you hit the X-rays up at say from 30 nanometers upwards, and you hit 1 nanometer, and then you get down into the realm of a distance they call an angstrom, which is that one with the A with the little circle above it. And 1 angstrom is 0.1 nanometers. And that's your gamma rays. So that kind of gives you an idea of the whole of the electromagnetic spectrum. And most of the output of the sun is in the sort of far IR through to the middle of the UV band. So to about 50 nanometers is most of your electromagnetic output of the sun. So that's kind of where it sits. I hope that's kind of a useful indicator of where the electromagnetic spectrum works and where we are on it. And anything 100 nanometers upwards is considered really bad, because that's the stuff that can break down atoms and therefore can break down DNA and cause genetic changes, which tends to lead to cancers, especially as far as UV is concerned, skin cancers. X-rays, because they tend to be absorbed more by bones than by skin, X-rays tend to cause bone cancers rather than skin cancers. Questions?
Yeah, I had one earlier.
Oh, did I miss it? I'm sorry, Terry. My brain.
Yeah, that's okay. I can repeat it. Because No Name thought I broke you. I can only go by what I've picked up on about light with sunlight, or light in general. When you put light through a prism and it breaks up into different light in different colours.
Yeah.
Is that a way of representing the different wavelengths of light, like what we're talking about here, or is this
Yes.
something different again?
Yes, yeah, very much so, Terry.
Yes. If you look at the breakout on the right-hand side of the diagram, which is basically the bit that's broken out from where it says visible in the long stack.
Yeah.
You'll see it starts with red at the bottom at the longest wavelength of 700 nanometers. And then it moves through orange, the orange and yellow colors into the green at about 600, and green actually occupies a big chunk between 600 and 500 nanometers. And then the blues sit in the 500 to the 400 nanometers, with violet right at the very top. So that's, yeah, so the greens mostly sit right in the middle of that set of wavelengths that define the visible light spectrum for us.
So if this light's coming from the sun, from the lowest to the highest, why do we have to manufacture our own machines that can do the infrareds and the microwaves and X-rays? Why do we have to? Why are we mimicking the light? Are we by doing those things?
Well, we can't always. A lot of the UV and the X-rays and stuff don't actually make it through to the surface of the Earth.
Right.
Sorry, just looking, trying to find the right. Just trying to find the right diagram. Damn, I can't see it. Ah, there it is. Did I? Are you seeing a different?
No, we've still got that one before, the one you've shown us a minute ago. Well, the same one we were just talking about.
Okay. I'll have to change the share. Sorry. Okay, so
Oh, that one.
so this one,
Yeah, I've seen that one once before.
this one shows what can and can't get from space down through to Earth
Can you make it big enough to fit the screen better?
let me try zooming that a bit.
Just fill the screen or fill the window you got there.
Yeah, that's pretty much filling the window I've got here now.
Yeah, that's good. That's good on this end now.
Yeah. Again, this is still asked backwards as far as I'm concerned from right. So remember, the longest wavelength is on the right hand side. So the lowest energy is on the right hand side. The highest energy is on the left hand side. And basically, the atmosphere stops long wavelength radio waves from getting in and also stops our long wavelength transmissions getting out. Yeah. Then there's a chunk.
What's the blue part of the screen in the window in the picture mean, and what's the green part mean?
Right, the green part shows how much is being blocked by the atmosphere. So if the green part is at 100%, that means that nothing of that gets from space to the surface.
Where it says 100 things on the end
Where
there.
it says 100%, which is about halfway up on the left-hand end.
Yeah, that's the left side.
So
But I'm on the. You said to look on the right-hand side where it says long wavelength radio waves blocked.
Yeah, and the amount that gets, so essentially, the dips show how much is getting through the atmosphere. So if you got down to zero, if you get down to 0%, all of it gets from space to the surface of the Earth. So sort of the microwave radio bands are really good because they all come straight through. They don't get blocked. And everything we transmit on those frequencies also goes straight out into space. So that's handy. the longer wavelength.
I think I might have needed a wavelength graph to understand the size of the wavelengths, like 10 centimeters
I'm going to pull that up for you in just a second. I might have to go back to default scene.
Because it's like as if we've got to go backwards in some of these descriptions we're talking about, because there's certain bits and pieces that you might be saying it, but then they have to be explained what certain things are before we can get to a certain point.
There we go. This is how we work out. This is a really good approximation, and it works in the right direction.
Okay,
As you see,
that's helpful.
The longer wavelength is on the left, the shorter wavelength is on the right.
Right, okay.
So we've got radio waves at around about 1,000 meters in. Yeah, we've got radio waves with a wavelength of around about 1,000 meters. So, approximate scale of the wavelength, the size of really big buildings like the Burj Khalifa and the Petronas Towers and those sort of size buildings, the really big buildings out there. They have, they're sort of 1,000 meters tall, and they're kind of like, that's your AM radio and your FM radio and your TV and what have you. And remember I said about the temperature of objects which the radiation is the most intense. So that's really cold stuff that radiates at that temperature. Then you start moving up into the microwave wavelengths. So typically 10 centimeter or less than a meter wavelength. So human sized. Yeah. That's sort of human sized is kind of your UHF TV. And your very early mobile phones worked at around the same sort of frequency stroke wavelength.
So just to add to what Alan's saying there, your VHF band of your amateur radio band, which is classified as your 2 meter band, that sits right around about the 400 megahertz, the 300 to 400 megahertz type area.
Yeah, and your early mobile phones were around about 900 megahertz, and they're kind of down to about a meter and a half, I think.
900 megs.
Yeah, go and get a calculator and
do the calculation. I'll have to. So it's divided by 3.
It's 3 times 10 to the 8 divided by 900 times 10 to the 6.
So you do it the hard way. I'd cheat.
So is it wrong to say that a wave, as in radio, as in that's sound? Is it, or is that different again?
Yeah,
not sound.
That's magnetic. It's not sound. Sound waves work in a similar way, but they are compression waves in the atmospheric gases. Electromagnetic waves are photons, or made from photons. Even the radio waves are actually photons, but because the photons have so little energy, we tend to treat them just as waves, and we kind of ignore the particle part because the particles just don't have the energy to be particularly useful as photons, as a particle, as sorry, not as particles, as units of energy rather than just looking at the wave itself.
So just for future reference, the quick, easy, rough and rugged way of changing your frequency in megahertz into the meter, or the measurement in a meter, if you just divide the frequency in megahertz by 300, and that 300 represents the speed of light, because radio and all of that and light waves, they're all interlinked. They roughly use the same law when it comes to the speed of light. So a nice, crude and inaccurate, however, makes life a lot easier way of changing the frequency into the measurement of the wavelength is the frequency divided by 300. And if you do that for, say, something like Alan said before, 900, which is your mobile, one of the mobile phone frequencies they used to use, that gives you a measurement of about 3. So that would be 3 meters.
My estimation was off a bit then.
Yeah.
Never mind.
But it's yeah. So.
But it's a human scale at least, isn't it? It's a distance. It's a distance we can easily relate to. You know, whereas you start getting into the microwave frequencies, you're then getting down to say 10 centimeters.
Yep.
It's sort of like exponentially that the waves change in the frequencies by the look of the graph here.
It's kind of logarithmic to a degree because obviously that's how we've actually divided it up. And when it comes to radio, the amount of different bits of frequency you need to be useful to send messages stays pretty constant. But as you get into the higher and higher frequencies, it's much easier to have that same chunk in something that's, you know, dealing with something that is 10 millimeters long when you've got to squidge it into 5 centimeters is a lot harder than dealing with something that is 10 millimeters long when you've got to squidge it into a kilometer. And you're talking about kilometers. You can get an awful lot more 5 millimeters in a kilometer. Which is why we tend to try and use higher and higher frequencies to do stuff, because you can squidge more useful stuff into bits of it, because you've moved from working with millimeters and centimeters to working with millimeters and kilometers. And that's how we tend to end up working with electromagnetic radiation. That's why, for example, we like using fiber optics, because we can push a lot more data down a fiber optic cable, because we're working in tens of kilometers, we're in millimeters per tens of kilometers now, and not just kilometers. as an analogy for distance. But as you can see, as we get up into into the infrared, the wavelength is the size of the point of a needle, and visible light is the size of pretty much single cells. And then, as you can see, as we move up, the issue with ultraviolet is that it's of a size of molecules and can cause damage to molecules. And X-rays are actually the size of atoms. Gamma rays the size of atomic nuclei. So they're the energy
what could be after gamma rays?
There isn't anything after gamma rays. Because you're essentially you're essentially about to hit the Planck. You're essentially about to hit the Planck length. I forget off the top. Where's so the Planck length is approximately 1.6 times 10 to the minus 35 meters. So, gamma, you're getting into gamma rays at 10 to the 20 meters. So, yeah, you haven't got a lot more space before you start hitting the Planck length. And that's basically the smallest size that you can have.
I was noticing on the temperatures of objects at which this radiation is the most intense wavelength emitted, and I was just reading the temperatures, and I know a K is for Kelvin,
Sorry.
but it goes 173 minus. It's minus 173 degrees Celsius. Well, what if it was 0 degrees Celsius? That's somewhere in between infrared and visible then.
We work on with black body radiation. It's always done in Kelvin, which is the SI unit for temperature. The freezing point of water is 272 Kelvin.
So it basically, Terry, falls right in that visible light spectrum.
Well, actually, the right in the middle of the visible light spectrum, on the bluish, just towards the bluish bit, is about 5,500 Kelvin.
Yeah, but I'm talking about if it's right at 0, the temperature.
Yeah, it doesn't. It's you're not gonna you don't get. You're going to be. I'm guessing you're going to be. You're going to be. On that scale, you're going to be barely the difference between 100K and 272K is negligible, because remember, you've got two lines there, that's 100K and then 10,000K.
Yeah.
And so you're squidging an awful lot in that. So 272K is basically pretty much where the red is pretty much where the black line is for 100K for the color that you get off of it. But sunlight is centered at around about 550 Kelvin. And it's interesting to note that the light that the electromagnetic radiation that we can sense with our eyes is pretty much the center of what the sun generates. Funny how evolution would allow us to see basically what the sun produces and not really anything else. Because why would it?
That means the evolution of the eyes going back millions and millions of years ago would have had to develop because of that reason, the sunlight. We don't know
exactly.
we don't know what the sunlight was like back then though either, because we were just talking about how the atmosphere can change
We do.
Change the light.
We do, because even if the atmosphere changes the light the sun is emitting, so the light that is getting here is going to be the same.
Hey, Renee and me, my middle name's Kelvin. That's not very nice.
Lord Kelvin, very, 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 very clever bloke. Actually, M-Ball, radio waves are modulated with other electronic signals usually, oftentimes which have been generated by converting sound to electricity. Sorry, pedantic head-on.
Yeah, ons and offs.
Yeah, or you can modulate it with ons and offs as well, of course. You don't have to use sound. And there's lots of ways of modulating all sorts of signals onto electromagnetic radiation. You don't have to just adjust the amplitude. You can adjust you can adjust you can adjust the frequency of the transmission as well. But that's not really a relevant discussion to the light output from the sun. Although it is, of course, all oh, sorry.
Was there any
lost
more?
Lost the thought there for a minute. Apologies.
Trying to see where we're up to now. Oh. Oh, there's your graph, Peter. I just found it. It was in Wikipedia, the one you posted.
Yes, it was.
Yes.
Well, you think I made that up?
Yeah. I was going to say, Terry, I wonder where I might have found all of these graphs, all of these diagrams that I'm showing you right at this minute.
I know I might have sent you a couple.
A lot of them came from Wiki.
What, the same page I'm on?
No, not necessarily the same page you're on.
Oh, okay.
But there we go. Now that is actually how an electromagnetic wave goes.
Oh, I don't think we can see that.
Can't you?
You need to share it, Alan.
Oh, I stopped sharing, didn't I? What a plonker.
Professor Phil said you're doing a great job, Alan.
Oh, brilliant. Thank you, Professor Phil. Sorry, it won't let me zoom that in. I do apologise.
Oh, how rude.
I've just had a sneaky thought. I can't zoom it in, but...
No, you don't want to zoom in, you want to zoom out.
There we go.
No, I couldn't zoom it in, but I just realised I can make the window smaller, and it's gonna make the window, it's gonna make the thing bigger in the window, isn't it?
Yeah, that's okay.
Yeah, no, I wanted to zoom into the image to make the image bigger in the window, but I couldn't. So
Okay.
I reduced the size of the window.
Okay.
But that's how electromagnetic waves work. So you have an the red is an electric field, and the blue is a magnetic field, and they work at 90 degrees to each other. And the wavelength we've been talking about is the distance between the peaks.
Yeah, the peak to peak. It
The
can.
peak, well, the distance between any 2 points that are at the same point on the wavelength. But the easiest way to do it is peak to peak. But you can actually see the wavelength marker at the left-hand end of that diagram going up and down as the wave moves to the right. I hope you can see the. Yeah, of course you'll be able to see the animation, won't you? So that's how it works for everything from the longest rate, from the really long wavelength, extra low frequency transmitters that were used by the US Navy for sending messages to submarines, and was used by the global ground-based navigation system called Omega, that pretty much covered the whole globe from 4 transmitters, admittedly using 400-meter tall towers, all the way through microwave, infrared, visible, UV, X-ray, and gamma rays. They all have this same um, electric field, magnetic field relationship, but carried by photons, which basically carry little lumps of energy, or at least that's how it can be thought of. If you don't want to get into the full super duper detailed maths of it all, which
No,
I can assure you,
not just yet.
which I can assure you we don't want to.
I'm trying to keep the basics just so we can breeze through it a bit.
Yeah, no, yes, but you see, the flurfers will always try and push it to bring up this, all the quantum stuff and all the rest of it,
Well,
because
I think we've gone a bit beyond, above and beyond some of the things that they even bring up.
Oh yeah, but I know what flurfers are like. You see, the flurfers. If you try and leave it at this level, they'll say, "But it's like they now try and like they screw with Newton and Einstein. This stuff still works. Most of the time, if you're an RF engineer, you think about this. You don't think about um, the four Maxwell's wave equations and and the fact that light is what light really is. You just use this because it works. It does the job for you. It gives you all the information you need to work stuff out and work in the real world. And yeah, mostly that's what's important. Which is why, from gravity's point of view, Newton still works perfectly fine as a force. You can use gravity as a force, and it works perfectly well, unless you get near to something very very big, and it's much the same with light and EM. And I guess I really shouldn't say flurfers. I should really say Gleam and his electric universe friends. That's who tend to really break this.
I've got to call out Dora. Hi, Dora. Hi, Stewie. Right, now we could, where Peter got the image from, the next section.
Bacon God, yeah, photons are a bit like hamsters carrying nuts from place to place. But they wibble and they wobble on the way.
Wow, this is getting into more deep stuff.
Well, this is actually what this is a lot of what we've just been talking about. That the sun's solar radiation is close to that. Remember that black body. Remember those black body temperatures we were looking at just now at the
Yeah.
bottom of the thing. Yeah. The sun is one of those with a temperature that people range from sort of in the mid 5,000s Kelvin. Because one important thing we remember is that Kelvin is not degrees; it's just Kelvin. We might have degrees Fahrenheit and degrees centigrade, but it's only Kelvin. There's no degrees. Yeah, it produces pretty much the whole gamut of wave of the EM spectrum, from low frequency RF all the way up to gamma rays. But what gets out is mostly that 5,000 K bit.
So the black body part is down the bottom end where you said radio and.
Well, no, yeah. Well, no. The what we get is centered on because a black body will radiate across a range of wavelengths. But it will, it's, well, technically an absolutely perfect black body radiator will radiate at its temperature and will basically radiate one wavelength of light. But the sun is pretty dang close as you're going to get in the real world to a black body radiator. So it radiates pretty close to at that temperature. I can tell you another really good black body radiator that we see every day, and again why they are so good for a lot of things, is tungsten light bulbs. They approximate very closely to a perfect black body radiator. And the hotter you make them, the bluer they get. And you can actually make them hot enough that they will replicate the sun. We call those photo floods, and they do take quite a lot of energy to get there. But the black body thing is what we get is very close to a black body, because it's basically a load of very hot gas.
All right.
So, yeah, and you don't get the gamma rays out because they just won't make it past all the stuff that's there without getting absorbed and re-radiated because they're the same wavelength as the things. That's the thing for photon to get absorbed. It really helps if it's of a similar wavelength to what it's going to interact with.
Yeah. So with what Alan's saying there, it's I'll use the word basic radio theory there. So the best way to tune an antenna to get the most out of an antenna is if you work out the wavelength of the frequency you're using. Generally speaking, you half that wavelength and you use a half wave antenna, and that will give you an optimized antenna length for that frequency. So, for example, if you were to use the old CB frequency of 27.200 megahertz, that works out to about 5.5 meters, and that's a known quantity that works with those frequencies, and that's how that whole calculation was worked out earlier, using the speed of light with the frequency to get the length of the wavelength to meter conversion. And like Alan alluded to just then, the same is also true for receiving. So if you've got a frequency coming in and you use something along the lines of a simple crystal radio, you actually tune that radio to that frequency. And one of the additional ways that you can help tune that to that frequency is tune your antenna length. And as you go into the smaller and smaller wavelengths, the higher frequencies and the smaller wavelengths, when they start interacting with at a cellular level and stuff like that, that's one of the ways they can use radio frequency to target different cells and stuff like that when they're using them on your body to remove growths and alike. And the downside is, like Alan said, that if they choose the wrong frequency, it can actually interact directly with those cells at a molecular level,
Which is mostly a bad thing. Because you have to remember that things like radiotherapy for cancer treatment, basically you use X-ray sources in multiple different positions, firing narrow beams that intersect at the point where the tumor is, and you just hope to hell that the X radiation kills the tumor cells faster than it kills the healthy cells around it. And fortunately, for early stage cancers, it works really, really well for a lot of them. Not everything, but for a lot. Because, hey, science, it works, mothers. Okay, science advert finished.
I need to give my eyes a rest to read.
all right.
Just trying to work out what.
Why do I feel like I'm
we're
talking an awful lot?
We've gone through all that. The sun emits X-rays, ultraviolet, visible light, infrared, and even radio waves.
Okay.
The only direct
So,
signature of the nuclear process is the emission of
Neutrinos.
neutrinos. Okay. Neutrinos is a fermion that interacts only via the weak subatomic force and gravity. The neutrino is so named because it is electrically neutral and because its rest mass is so small that it is long thought to be zero. The mass of the neutrino is much smaller than that of other known elementary particles. Wow.
Yeah, because neutrinos can travel at very high proportions of the speed of light.
I've already gone through ultraviolet. The red.
Yeah, I mean, I've talked about most of that already. So
On solar constant. Flux density. Flux describes any effect that appears to pass or travel through a surface or substance. A flux is a concept in applied mathematics and vector calculus which has many applications to physics or transport phenomena. Flux is a vector quantity describing the magnitude and direction.
yeah, so why we have is why we talk about lux, which is lumens per square meter, or we talk about watts per square meter, because we're talking about energy arriving at some imagine, because it can be an imaginary surface. It doesn't have to be an actual surface. So, oh, I like that one. I'll have to get that one as well.
Yeah,
Find out
that's
where that one
cool,
is.
that one. Light or visible light is electromagnetic radiation within the portion of the electromagnetic spectrum that can be perceived by the human eye. Visible light is usually defined as having wavelengths in the range of, that should be
700 to
700 to
400
400
nanometers.
nanometers, um,
Yeah.
or that other number underneath it.
4 times 10 to the minus 7 to 7 times 10 to the minus 7 meters.
Yeah, that's what always fascinated me when I was younger, with the prism effect of a light coming through it, and where did all these colours come from that come out the other end?
out of the white light.
Well,
Yeah.
actually what you're seeing there is classic chromatic aberration. Something we really don't like as photographers.
So, just a little bit of a story along those lines there with the prism that you've got there, Terry.
Dora, it wasn't really a presentation. It's me just responding to the stuff that's on the screen.
I took my younger daughter down to the Woo Woo Crystal Shop the other day.
Oh, the Woo Woo Crystal Shop.
But Woo Woo crystals look nice, don't they? I mean,
little girls love Woo Woo crystals because they're pretty, and that's why she buys them.
I was going to get the polarizer and put it in my Commodore to make it go faster.
Oh, the Peter Bock polarizer.
Oh, yeah.
I've got the picture of that somewhere.
Yeah, I had
I've
a
actually
picture of it somewhere too.
There's a guy down here in Melbourne that's got a VK with it, with the original factory fitted one.
Yeah,
it's one of the blue meanies.
Yeah.
But anyway,
yeah.
So we went down and we found these wonderful crystals. They were somewhat square in shape, but it was a rhombus, but a cube, if that makes sense. Is that a good describing it?
A bent cube.
So a cuboid rhombus. So
So the angles aren't 90 degrees. They're
an askew square.
Yeah, like a cardboard box that's been pushed over a bit.
Yeah.
And because it's a pure, it's a crystalline substance that's pure to the nature of that particular crystal. the light refraction through it at different angles actually gave you a rainbow, similar to the effect of a prism. So
yeah, well, they are basically a prism, because a
yeah,
prism is any a prism is pretty much a prism can be pretty much any lump of something that light passes through.
well, look, we all know the old fish tank can produce a rainbow effect. You know,
Yeah, as long as you get
any beveled glass can give the rainbow effect as the light transfers through it.
basically you need what you really want is a couple of different angles of incidence to really spread the light out well. Which is why triangular prisms are good, because they generally give you enough. It's generally easy to get acceptable, usable angles of incidence going in and coming out. That's what you need. You need it to have the two different angles of incidence. If they come in and the two surfaces are parallel, then it's really difficult, because what happens is the light goes in and then comes out. It might get translated slightly, but the angles are going to be much the same. They're going to be going in the same direction essentially, and so you don't see nearly as much of the dispersion.
Okay, Einstein. If a prism's got flat sides, how can we see rainbows through water droplets that are round?
Internal reflection,
Ah.
because it's all to do, and of course also the fact that as they're semi-spheroid, the light is the photons are actually all having different angles of incidence, aren't they?
Yeah, but is the light
So
reflecting off the raindrops or through the
So
raindrops?
it's
the
a bit of
light,
both. It's a bit of both, Terry. So because
what
of the
happens
shape.
is, go on, Peter, you talk for a minute.
Okay. So because of the shape of the raindrop itself being somewhat close to being symmetrical, the light will come in from one side, normally with the sun behind you, and the rain falling in front of you. The rain will go into the raindrop, be magnified because of it going through the different densities, and the shape of the raindrop itself works a bit like a lens. However, when the light hits the opposite side of the raindrop, it's reflected back towards you. And when this process happens, it works along the same idea as a prism. So it's a combination of the lens effect and the refractive and reflective properties of the raindrop itself.
You were going to say refraction, weren't you?
Did I say density?
He said refractive. Peter said refractive and reflective in the correct places.
Yeah.
Oh, I got it right.
Yeah,
Yay me!
I think at one point you almost misspoke.
yeah, I was waiting. I was listening carefully. I was
Oh,
listening.
I,
blah
I,
blah 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 blah.
but that's why I love doing this here in a situation where, let's be honest, people can hang crap on me out in the stream, but I've got other people, so that if I do make a misword or a misspoke, I can get corrected before it becomes somewhat embarrassing.
You might have lost me on a lot of this other stuff you were talking about. When you're talking about refraction and reflection and all that sort of
Okay.
stuff, I can keep up with you.
So if you look at the picture that you've got on the screen at the moment, Terry, of that prism.
Hang on, guys. I think we're both wrong, because Professor Phil has posted in the side chat. It's because of total internal reflection and diffraction.
Diffraction, is it? Diffraction.
Yeah. Okay. Yeah, I'm no physicist, and I'm winging this, so I will happily admit my error, and I'll be glad. I'll be glad when Professor Phil gets here because I can stop talking and he can start talking.
All hail Professor Phil.
And I was going to say that because that's what I had learnt from prisms about the internal reflection and diffraction. I just forgot the word diffraction.
It's well, you know, prisms. I always thought prisms worked on refraction, and of course, if you shine the light in at the right angles, you can also get total internal reflection going on.
Yeah,
and make the light come out in really odd directions. But you'll still get the light spreading if you get the angles right.
I knew it was
Professor
reflection.
Phil's threatened to come in here to correct us.
Oh, I hope so. I knew it was reflection because otherwise, the way that the sun comes, like I said, over the top of my head, hits the raindrops in front of me, but I can see the
reflected
the rainbow in front of me. So for that to happen, it has to be reflected towards me within the raindrop itself. But I'll be honest, I will defer to the, shall we say, expert, because I obviously got diffraction and refraction mixed up.
Yeah. Well, at least I haven't made any really serious mistakes yet.
That's all right. That's why we got Professor Phil.
I lost
because I'm pretty sure I would have got stopped before I went too far down a wrong path by the professor banging something like chat.
I bumped the key and now I lost my picture. Oh no.
Wait, you've gone right. There we go.
That one, yeah. Phew. There it is.
Okay, so I need to get the wiki. I need to get the sunlight wiki.
I'm just trying to get it so it fits on the screen. I'll get there. There we go. Now bump the key. Definitely must be a coffee break. Smoko break, everyone. Hard work.
Do. Oh no, we could always put the test pattern back up too.
We had popcorn too. So somebody out in the peanut gallery cooked a two pounds of popcorn.
Because if we're not careful, I'm going to need to do a Riley.
Have you got a Gatorade bottle?
No, and unfortunately, my orange fizzy pop bottle is still half full of orange fizzy pop.
Yeah, not.
I know. There's not a lot of difference between what's in the bottle now and what would be in the bottle afterwards.
Lucky you're not colour illiterate like me in a way where I get too confused.
I know from personal experience, the Gatorade bottles work better because they've got the bigger opening, so you have less spillage.
We don't see Gatorade a lot in the UK, though. That's the problem.
Well, you have some other type of sports drinks that's got those big mouth opening type.
Yeah, but not in the 2 litre bottles.
Yeah.
And I know.
What you're going to fill up a 2 litre bottle in one go?
I'll tell you what. One of them 500 ml like sports drinks bottles. That might be an issue. Sorry, this conversation needs to stop now. I've just realised.
It's all toilet humour now. It's fantastic. Straight down into the gutter.
Well, I said we're on a break for 5 minutes.
Literally in the gutter.
No gators. What? So we use Professor Phil to make the really bad mistakes then? What do you mean, Andrea?
No. we use Professor Phil to stop us making really, really bad mistakes.
Lucasade bottle.
We'll
Lucasade bottle, yeah, okay, a big. I think they do a wide neck
Yeah,
1
they
litre Lucasade bottle.
Well, just put it this way: if I was here on my own and I didn't have Peter or you, Alan, I would have had Professor Phil out there going, "Look, let me in. I'll fix you, Terry."
Yeah,
Because I would have screwed it
yeah.
all. I
Anyway,
would have screwed it all up.
I'll be back in a second,
all
or
right.
maybe a minute.
Well, if you travel at the speed of light, you'll get back at less time, or close to the speed of light, which we hadn't actually covered yet.
Oh, well,
Yeah, we hadn't. That's another part we didn't mention.
not really. Yeah, so
If we
I
cover
suppose.
we cover too much in this topic for tonight. We won't have to do it to do light again, part two.
Well, that's
Well, I'd like to leave part two for other things to do with light. But if we want to keep it on the flat Earth side, yeah, there might be. I don't know. I'd have to think about that one. We need a flat earther in here.
Wouldn't it be good to actually try and get one of these flat earthers that profess to know their science or their knowledge of the world to come and explain some of the reasoning and thinking that they've got for some of these processes that just couldn't work on a flat earth.
You're not suggesting to go spy on a Discord again, are you?
Oh, well, I'll be honest. I was in Team Skeptics chat today, and Becky from Australia, she
Oh,
was getting quite upset at me.
and you want a little bit of fact about something? Have
Yeah,
you ever seen
there we
Becky in
go.
Australia on Team
Back again.
Skeptics chat before?
Have I ever? No, actually.
Oh, okay. We were on Gem Pandas the other day, and Becky from Australia met Nathan Thompson.
Did she?
Hint, hint. Nudge, nudge, wink, wink.
Ah,
Ah. So I'll just leave the rest up to you to figure it out in your own imagination, because they went off in their own little world into a DM, and ever since then they seem to be bosom buddies. Because everywhere I go around looking, I seem to bump into Becky and Nathan.
well, funny enough, Nathan was in the chat at the same time,
Oh, exactly.
and it was almost like she was trying to white knight him,
Yes, exactly.
and like I was somewhat polite. I didn't get rude or anything like that, but I did ask her some serious questions, like, how the heck can you be a flat earther in Australia when nothing on the map works in Australia? How can you
How?
just explain that to me? If you want to meet me and have a chat, that would be wonderful, and please try and convert me, because I'd like to understand how you can think like this.
Well, she left me server, so how's she going to do that now?
Oh, she left the
She
server.
was on our, yeah, she was in my server for a while, and then now she's disappeared.
Oh.
Oh dear. Irish Stew says about Professor Stanley
I'll be
Unwin.
back in a minute. Alan went, so I've got to go.
All right, you go, Terry.
Is my audio okay today?
Yes, it's beautiful, actually. It was clipping a little bit earlier, but it sounds nice now.
It's really weird. You know why? Because I have my audio set up funny, and I've had the audio coming out of the monitor speakers the whole time,
Oh,
not my headphones.
it sounds perfect. There's no feedback
It,
or
it,
echo or
it,
anything.
Well, at the minute it's great because I've got my headphones. I don't have to have the bloody headphones over my ears anymore. I think it was coming out my headphones too, but I don't know. But it's working, so I'm not going to complain.
And what did Irish Stew say?
Have you heard of Professor Stanley Unwin?
Check him out. He explains things better than Flirts. Oh, so Irish Stew, does he explain it in such a way that the Flirts should try and explain their flat Earth, or is it?
Oh, I'm sure Stanley Unwin could explain flat Earth perfectly because it's it's an explanation somewhat like the explanation of the disc and whatever it is thing that the thing out of the engine that General Motors tried to invent. The
Peter Brock. It used Woo Magic and crystals, and Terry was just talking about it before.
He talks
the polarizer.
Good.
The polarizer.
Possibly.
Yeah.
He just talks a load of. He uses like. It's the thing that
the disc and capillary vibrator.
Yeah, that's the one.
Yeah,
it's a bit like that.
On it, like the microphone's not working, a thing like that. It's good.
It's like quite
mixes
funny.
all the words up and things. It's funny. I haven't heard of him for years.
Uh-oh. What's wrong?
The teacher's here.
Oh.
Sit up straight. Chewing gum out.
Oh, we better wipe the board. Quick! Put away the books. Put away your notes.
It's all right. I've stuck my chewing gum under the table for later.
Yeah, I did too. Yeah.
Behave yourself now.
It wasn't me. It was the other bloke.
It was Alan.
Hey, how are you going?
G'day,
I hope I didn't make too many mistakes.
G'day, Professor Phil. How are you?
Good. Now, listen, before I start, Alan is doing a fantastic job.
Teacher's pet.
That's the apple he gave him earlier, Pip.
Yeah.
Alan,
I had an hour of listening to him, and it was really a really enjoyable hour. Thank you, Alan.
Oh well, thank you very much. That actually means an awful lot coming from yourself.
No, it was very informative.
Don't I get any credit for bringing the topic up?
Absolutely. Okay. You still got to finish your assignment though, Terry.
Well, this might be only part one. I might have to do a part two.
Yeah. Okay. So one of the questions I heard was with regards to total internal reflection and diffraction. So
yes. Sorry, I got that wrong.
Why does a diamond shine so beautifully? Why does everybody love a diamond?
It's the light beam coming out of it that makes it look so shiny.
It's got multiple surface for internal.
Yeah, it's the total internal reflection. So what happens is it's like the diamond is able to capture a photon and keep that photon going over and over, reflecting inside, backwards and forwards in the diamond, which makes the diamond looks as though it's actually got a fire inside it. And in fact, one of the best examples of this is called the star sapphire and star ruby, which are both corundums.
Yes,
and,
please.
You find those in Sri Lanka and India sometimes. They're unique to those areas. And again, it's this total internal reflection. Reflection that causes this brilliance. But the diamond has something extra. It's not just got total internal reflection, but it's also got diffraction. And the diffraction is what causes photons to separate from each other. So you had this lecture on on electromagnetic radiation from Alan, which was perfect. And as he told you, right dead center of the continuum is visible light, which is really just a slither. Think of that about as being as thick as a piece of paper or less. So a very, very small slither of that happens to be visible light. And it's this visible light that's broken up into many different wavelengths, including all the way from red all the way back to violet, so to indigo and then violet. So when you're looking at diffraction is a means of slowing down these packets of energy in such a way, or changing their speed in such a way that they'll actually break up into their various distinct wavelengths for each color. So when you're looking at a white shirt like I'm wearing, why is it white? It's white because it's reflecting all of this of that entire spectrum. Why is a shirt blue? Why is something red? It's because it's absorbing everything else and reflecting only that wavelength. So in a nutshell, that's a drop of water. A drop of water is kind of almost like a prism. It's a very crude shape, for a prism. So it's like a droplet of water. If it was a complete circle, it wouldn't have the same effect. But again, total internal reflection and diffraction. That's it in a nutshell.
And correct me if I'm wrong, Professor Phil, that's one of the reasons why rainbows do have that, shall we call it quite often they're not that very bright as it would be in the sky, because the raindrops themselves don't make a great prism. However, they work enough to create the illusion of the rainbow.
They do, and but one of the amazing things about light is that even though individually, they'll create the entire spectrum, the entire light from red to indigo. However, when you look at it, you see they sort of the rainbow is actually broken up into the colors. You've got to be asking yourself, how come it is that if the individual droplet produces all of the colors, why aren't they jumbled up when you're looking at a rainbow? And it's simply this. It's got to do with the angle of where most of the light, the photons, is coming from. That angle just happens to be able to separate out the colors. So how can I explain it? So the rainbow, so that as the droplets are coming down through that, it's in the ones that are, if I can remember, I think the rainbows are red at the top and blue at the bottom. You can correct me on that if I'm wrong. So as the rain's coming down, as the light is going through these prisms, the ones that are higher up are producing a different wavelength to as a nominal wavelength to the ones that are lower down. So that's why you get this differentiation. That's what basically makes the rainbow the way that you see it. Now, why is some rainbows darker than others? That's got to do with the saturation of the water, the more there is, the brighter the rainbow will be. And of course, obviously the light as well.
So obviously other factors would be the size of the droplets, the intensity of the droplets,
all of that.
how much sun's actually hitting it directly.
Yeah.
Yep.
So people say sometimes that it comes down in buckets. Droplets generally are a particular size, and physics determines the size of a droplet.
Yes. However, and we all know that you can get a misty rain, which is not quite water droplets. It's vapor basically floating in the air, or you can get, the big fat droplets that we know as rain.
Oh, yeah, exactly. And you can even get fog.
Yeah.
Okay, which is which is another thing. But really, it's to relate this back to the flat Earth thing. So often you hear flat earthers people say, well, you haven't been to the sun, so you don't know what the sun is. Well, the thing about it is that because of our knowledge of the electromagnetic spectrum and being able to actually look at it and determine what is this that's coming from the sun, how can we have a look at particular energy levels from the sun? And we have what we call spectrometers, of course, because now we can have a look at the spectrum.
Just slow down a little bit. Oh, I can't go that quick, Professor Phil.
That's all right. Yeah, so, all right. So we can look at the spectrum that comes from the sun. And we can see it. What happens is the spectrum has spectral lines, dark areas, dark lines in it.
Okay. And on screen now, Professor Phil.
Yeah.
There you go.
Okay. Oh, there you go. So can you see the spectral lines? So you can see now, these are particular to elements. So you can see the one for hydrogen, where you've got the red, you can see that particular spectral lines that represent hydrogen. So we have spectrometers that can actually do this. And this is marvelous technology, by the way, that mostly came from Australia. I'll tell you about that in a minute. The company over here called Varian Tektron. Now, if you have a look at this, you can see what sodium looks like, for instance. You can see what hydrogen looks like, okay, with these spectral lines. Now, we can actually look at what helium looks like. And guess what? When we look at an abundance, because you can actually look at that this is just looking at, without considering the abundance of hydrogen. When we look at that in terms of abundance, we can see that there's really only two main abundant elements. There are other elements there, but there are two main abundant elements, and they turn hydrogen and helium. And we can actually see from the abundance, we can calculate how much there is of one compared to the other. And because of that, we know how old the sun is, and we know how long it's going to last. So we know that the sun eventually will become a red dwarf, and all of the hydrogen will be used up. And as it does that, it will eventually die. So it's this spectral lines. Now, what Varian did, so this is the Australian company Varian. So even as a young chemist, I was working with Varian to try to help perfect this. And what it is called atomic absorption spectrophotometry. So again, there's a prism, if you like. Prism is able to we're able to use the prism to focus a particular wavelength.
Hang on, Professor Phil. I've got another one coming up.
Sure.
I'll go as quick as I can.
That's okay.
You're struggling, Pete?
Oh, no, just trying to be in 6 places at once, you know. Professor Phil speaks a lot quicker than you do. But it's all right because I've got the screenshots for him.
Oh, great.
Oh, look at me go.
Oh, look at that.
Look at me go.
Oh, you guys are geniuses. Oh, my God. That's it. Okay, so there you go. There you've got helium and you've got iron. Okay, so the spectral lines for iron, Fe underneath that, and you can have a look at, so you can see how that goes through a slit. And so what we can do is we can actually maneuver the prism so that the prism gives us the particular wavelength that's particular to iron atoms when they're excited. So therefore we can have a look at not only that, identify them, but also check their abundance of those ones. So therefore we now have an instrument we turn the element, the sample into a gas. that allows us to heat it up and excite it to the point where it will release its spectral lines via through its photons. And then we can have a look at these can be compared to what's in the compared to what's coming from the prism, and bingo, you've got an analysis of the sample that you've got.
So, Professor Phil, as when I was younger and at a well-equipped high school that had a semi-decent chemistry section, we did something very, very similar to this using a prism. However, we used a Bunsen burner and a piece of wire and each of the different salts on the wire. So we'd moisten the wire. We'd put the piece of wire into the Bunsen burner, and then we'd set up light shields, so just black cardboard to prevent the other light getting through the prism.
Yes.
And we could record those lines for a short period of time on a card that the light was being transferred onto. So we could actually see the lines themselves of, for example, sodium.
The orange light,
the orange light from sodium, and then it went through the prism, and then we'd see it broken down into its different spectrum. That's the similar.
That's exactly right, and that prism is exactly what constitutes a spectrometer. Okay, it's this prism that's in a spectrometer. Now, a professional spectrometer, you can make adjustments to this prism. In other words, you can turn this prism. Okay, you can turn it so that you get the right wavelength. So it's even got a digital readout on it, so that you can see which wavelength is facing the prism. So in other words, you can turn the prism in such a way that imagine if the light was going through a prism and you could see like a rainbow. Now you wanted to only look at, let's say, the green stuff out of the rainbow. You would be able to turn that prism in such a way that the green one faces the slit. You see the slit that's there?
Yep.
Okay, so the green light faces the slit. All the other light isn't there. So if you knew what it was for sodium, you could face that so that you could see so that the sodium light heads towards the slit. Now, the amount of intensity of that light will give you the abundance of how much sodium is there in that particular solution that you try to analyze. But what you just described now is classic physics experiment or chemistry experiment that shows you that if you excite the electrons, you will get a particular color. Why do you think we have neon light, krypton lights, argon lights? They're all different colors. When you go to the shopping center and in Hong Kong, you can just about every color under the rainbow. They've managed to put enough gases together and excite them, that's the noble gases, to produce these colors. And that's just exciting these electrons using electricity.
And then obviously you've got the phosphorescent coating on the tube itself, which they use to blend with the color from the light and the color from the phosphorescence to get a combination of different colors.
Exactly. So actually, just like anything, there's really only three primary colors we have to worry about, and that's RGB. Okay, so
red, green, and
blue. It's not here tonight.
So that's the only three colors that we have. So of those three colors plus light plus black, you can make 256 million colors.
And black and white's not really a color. That's
no. Black and white just represents no reflection of any of the photons of visible light, that is, and white means reflection of all of the photons of visible light. That was a really enjoyable. Is Alan still there?
Yeah,
I'm still here.
Okay, Alan, that was fantastic, mate. I really enjoyed that talk that you gave everybody. I had an hour's drive home, and it was a very enjoyable hour. Thank you very much.
Well, Not bad considering I was doing it off the top of my head.
No, I could tell you were winging it, but you did it really well, like those aeroplanes.
Well, I was cheating. I was going from Wikipedia first.
Yeah.
And I'm glad that you finished there, Professor Phil, because I'm pretty much out of slides now.
No, that's it. Yeah.
I've just been trying to work out where to go to from here.
Yeah.
With the light. I'm looking in Wikipedia. I'll share Wikipedia, that way you can see.
It depends. It depends on if you want to talk about light or if you want to talk about sunlight.
Yes. Well, sunlight's a particularly interesting version of light, isn't it? You know.
I don't want to talk about light like a torch or a light bulb light. It has to be from the sun, obviously, if we're talking about the sun's light.
Well, for instance, I was actually going to do a little video on this, and that is, like the two equations that represent the Doppler effect. Okay, so one of the equations is the difference between one equation and the other is just a plus and a minus sign, and what they represent is what is the velocity of something that's coming towards you. It could be light or it could be sound that's coming towards you from a particular distance based on its wavelength. So you're looking at its wavelength, because its wavelength will change as it's coming towards you or change as it's heading away from you. And it's this. So flat earthers often say, you don't know how far the stars are, or you don't know how old the universe is. Well, it's because we know how wavelength can change with respect to time and distance, that we know exactly how far away it is. And also, we therefore know, because we know the speed of light, we know how old it is. This is something I just can't get over to flat earthers.
Yeah, but why is that not surprising? I mean, let's face it.
Yeah, I know. Yeah, they wouldn't be flat earthers if they had the intellect to actually assimilate that. Yeah, you're quite right. I keep forgetting that point.
That's actually one of the reasons why I prefer some of these conversations that sparked off by things they say, but are not just directly addressing the things they say. Because we learn far more stuff about all sorts of things this way.
Yes. Yeah. Well, the flat Earth thing has really, the positive side of it is so many people have started becoming interested in physics who've never been interested in it before, who've never looked at it before, and even when they're wrong, it's still there's still bits and pieces of it that they get to hear and get right, even if overall they're still stuck in their cult, if you like, and they don't want to change. They're still listening to the physics and they're still talking about it. And one of our biggest problem with science is that we've treated it like something elite, and we tend to use that language like that, and that is why science isn't as widespread in the lay community as it should be. And that's simply because scientists either don't talk at all, or they talk in what lay people would call riddles.
Yeah, that trying to keep it accessible is really difficult at times.
Can I just steal the screen for a minute, Terry?
Yeah.
No, it's all right.
You can't actually steal it. I have to actually stop.
You have to allow me to steal it. That's correct.
Yeah.
That's why I asked politely.
Yeah, and I've got to put it back to Zoom.
You have to borrow it rather than being able to steal it. Only Terry can steal it.
Yeah.
There you go, Professor Phil.
Yeah. Okay. Yes. Yeah. Exactly. Master lines of metals. Yeah. Calcium, iron, magnesium. The sun's composition similar to the Earth. There you go. Hydrogen, helium form strong lines. Yep. Okay. Perfect. That's it. That's the whole story.
And what machine did we use to figure this out?
So it's the same as what I showed before on screen, Terry, where we put the light itself through a prism from a slit.
Mm-hmm.
And by working out the frequency of the lines, please correct me if I'm wrong, Professor Phil. By working out the frequency of the lines on the shown on the lower half, so each of the different elements below the two lines show the elements that have been represented in the light that's coming from the sun on the above in
Yes.
number one and number
That's
two.
it. Yep. So that's how you can tell what they are, but you can also measure their abundance. So that
Abundance, yeah.
So you can see 73% hydrogen H1 and 25% helium. So we've got still a bit of life left in the old bird up there.
Yeah.
And 2% everything else, but there is a lot of everything else. So you can see it kind of gives us an insight into how this universe actually came into being. So when we talk that they didn't come up with the Big Bang, but just on the back of an envelope. All of this evidence that you looking at right on this screen, all put together, comes to came to the conclusion that the Big Bang is probably how all of this happened.
And this, what we're seeing on the screen, is where the whole saying that we're all made up of stardust, because the elements that you see on the screen here are the same elements that we find on Earth, the same elements that we find within ourselves.
Yes.
They're the same elements that are on in the sun. So, in essence, what that shows is that our planet itself has come from material that's come from other suns.
Absolutely, 100%. So what you're looking at right over there, when you're looking at the sun, is you're looking at, if you like, a great big factory. Okay, so it's not only just producing helium, hydrogen producing helium, but look at all the other things that's, even though they're small in abundance compared to the helium, they are actually being created there. Eventually, the sun will lose all of that helium and become a dwarf and explode. Eventually, all of these things will coalesce, and you will get more planets. So this is the cycle. We can see that this happens, so we can look using the electromagnetic spectrum, using redshift, using wavelength, frequency, all these things that we know about it, to be able to pinpoint the age of things. And we can see how it is that they formed. And if we trace that back far enough, we can see where the universe actually started. So it's the 13.7 billion. We didn't make that up on the back of an envelope.
Another indication that maths is a great thing.
Yeah.
Yeah. And the fact that the sciences progress with improvements in engineering that allow us to measure things with more accuracy.
Yes. Well, you think about it. I mean, you know, as you were describing, Alan, on my way here, you were talking about things being, like wavelengths, being nanometers. That's a nano means a billionth. Okay, so a billionth of a meter. So if you think about a millimeter, and then you cut that up into, so that's 10 to the 3. Then you cut that up into 1,000 more. That's 10 to the 6. A thousandth of a millimeter. Now cut that thousandth of a millimeter into another 1,000 pieces. Now you have a billionth.
Yeah. 10 to the minus 9. It's an awful lot
10
of
to the
zeros.
minus 9, exactly.
An awful lot of zeros before after the decimal point.
Yeah, exactly. It's a very, very small amount. And just to relate that back to pH, which is the video I did before, When you think about the pH of a solution being 7, in other words, 7 is the solution, it's 10 to the minus 7. That's how many free hydrogen ions are in that particular liquid. It is so small. Now, if it's got such a small amount of to make it neutral, like pH of 7, imagine how easily you could change that with just one single drop of acid, for instance, or one single drop of caustic. You could just change that pH so quickly. This is why it's such a small range. We're talking about such small numbers.
And I think that's one of the areas that some of these individuals that have problems understanding it, some of these numbers are so small, and others are so big that they're
exactly.
They become very hard to fathom, let alone understand in just a relative term. I can remember my science teacher once trying to explain it in a matter of fact way of
publisher.
A matter of fact way of saying, if a grain of sand was 1 mole, a glass of water would be the equivalent of every single grain of sand on an empty beach that you're standing on.
That would be an understatement.
Yeah.
I would say that if you picked up 1 grain of sand, there wouldn't be that many. There wouldn't be 6.02 by 10 to the 23 grains of sand on the beach.
Yep. Yeah. He used that example as a way of saying that the numbers that we're talking about here are just so astronomically large, and the differences are so astronomically small.
Yeah,
it becomes extremely hard for you to fathom without using this exponential number, so that you can have some type of a realm of an idea.
Yeah. Well, if you use that idea, and now let's just look at some of those charlatans that they call themselves homeopaths, right? So if you use that, and then you go to this homeopathy where they say, well, they're going to dilute something by 10 to the 100. Remember, we were just talking about 10 to the 23, right? Okay, so they're going to dilute something like 10 to the 100. That's many times more than 10 to the 23. Well, that would be akin to taking a drop, to taking a single grain of salt, going out to the Pacific Ocean, dropping in that bit of salt, and then claiming you made the sea salty. That's the kind of scale we're talking about. So how pathetic is that? There would not be a single molecule of the stuff that you're giving to somebody in 10 to the 23 if you had a dilution like that. You could not calculate a single molecule. Now, that is ridiculous, because there wouldn't be there would be no liquid solution anywhere without a single molecule of almost anything. So the complete practice is just nonsense.
Yeah, it all comes down to scale. And again, something else the flirters can't comprehend.
Yeah. Yeah, that's what it is. It's scale. Yeah. Yeah. And that goes for the universe. They think they say the stars haven't moved, and I can't seem to get this through to even people like Gleam or whatever. The stars haven't moved. Well, the stars are a bloody long way away. You would notice something moving if you're along the ground, if your nose was right at the ground. But if it's so far away, it'll take a lot of moving before you'd notice it.
internal chat, Terry.
Oh, and to just change the subject, we now, of course, get lots of hassle because the Bohr's model of the atom is good for a lot of things, but again, the flurfers, the electric universe people, they all go, but it's been superseded by something really complicated that becomes very difficult to understand unless you can do the calculus.
Oh, look, I can explain it in a simple lay term. What is so what you're looking at over there with the atom that's on the screen now is pretty much an example of Bohr's model. Okay, where you've got different electrons will be at different energy levels. All right, so that was his model, which is a bloody good model. And by the way, a very good way to work things out generally if you want to get some results. So it's not something we're going to throw away anytime soon. However,
it's kind of the model that I always think of because, like you say, it's great because you can bump an electron up and
exactly. It's a beautiful model, represents pretty well and suits the periodic table.
Give off another photon of particular energy level.
Yep.
And really handy.
Yes, no, absolutely. And explains the spectral lines and all that sort of jazz as well. Now, the thing about it is that the reality of it is that now that we have, we have the means to have a look at it a lot closer, what we can see is that it's actually a cloud. So in other words, these electrons can kind of be anywhere. But what makes Bohr's model still stand is that how do we know that there's one electron in the outer shell, or generally speaking, say in the outer shell of sodium? All right, so sodium is going to share an electron with, say, chlorine to make sodium chloride. How do we know what it is? Yes, it's a cloud, but guess what? The probability of finding the electron, a single electron in its outer shell, if you like, is still the highest. In other words, you've got the highest probability of finding an electron in this particular location off the cloud. So yes, while there's been some tickling around the edges with Bohr's model, the fundamentals of the model are still perfectly intact.
Well, as I said earlier, it's exactly like Newton and Einstein with gravity, isn't it?
Yes. Yeah, exactly. You can't throw Newton's stuff away. I mean, for goodness sake, I don't think about Einstein when we're putting a satellite in space, except of course with the clock. But it's the only time we ever think about it if we've got an internal clock and we have to synchronize a clock with the satellite. That's the only time we ever think about relativity. Otherwise, we're thinking about Newton and Kepler. That's how we know where to put the thing.
Yeah, and it's fine to use F equals ma and call it a force.
Totally, absolutely agree. Because I mean, what do you need for a force? You need what? You need a scalar, and then you need the vector. So you're going to multiply a scalar by a vector, and you're going to end up with a vector. So force is a vector. Mass is the scalar. Gravity's got to be the other one, the other vector, doesn't it? Where else are you going to get the vector from? If you end up with a vector, because you know force is in a particular direction, mass you know is a scalar, it's not a force. So the only other thing that's there is G. G has got to therefore be a force. It's got to be a force.
Yeah.
It's as simple as that. So now, if you relate it back to Einstein, Einstein will look at it and say, well, I'm going to explain why it's a force. It's only a force when there is mass distorting the space-time. In other words, without mass, you can't talk about gravity. Gravity isn't a thing to talk about unless mass happens to be present.
Yeah.
Okay? It doesn't exist but when mass is present. So in other words, because gravity is the distortion of the space-time. Why do two masses want to attract each other? Because they are both trying to get into this single distortion of space. Therefore, they must attract each other. Newton and Einstein worked perfectly together. How they can say one destroys the other is completely ridiculous. I can't imagine. It just shows total ignorance of how this works. I guess you can see I'm a bit passionate about this.
Yeah, of course. It's what you've put an awful lot of your life into teaching, isn't it?
My whole life.
And working it. Yeah. I mean, your whole working life will have been this. And when people then come out and completely distort it and
Not
talk
only
rubbish
that,
about it, you're going to get
people
a
like
little
them.
bit cross.
I don't mind being corrected by my peers. I don't mind at all, but or even a layperson, no problems. I can I can get it wrong. I can, your lecture today on the way home was brilliant. I loved it because it reminded me of stuff that I'd forgotten about and that I haven't thought about for my students. And I thought, wow, I'm really enjoying this. And now, but if a flurfer comes along and then says, "Oh, Professor, you're a nut," or you don't know what you're talking about. Hang on a second. I've been 46 bloody years doing this. And you've been there for 5 minutes.
Yeah. And you've done, and it's not just sitting in a university lecture theatre indoctrinating the students. You're also out doing practical stuff like putting things in orbit, so that they
practicing
work.
The physics.
Yeah.
The thing I find somewhat humorous, Professor Phil, is the way that science works. It can explain why if I bang a tuning fork on this side of the room, it can explain why a crystal glass on the other side of the room will break or vibrate at the same time, because the two elements are tuned to the same frequency. And it works the same way as radio does. These things are all explainable by math, explainable by science, explainable by physics. And these can be done in front of you. It's not magic. The same science, the same physics, the same math can explain the Earth. And for them to disavow and or ignore this math, science, physics, and any other of the sciences that go with it is paramount to saying, like Big Blue has said so many, many times, la, 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 la,
Yeah, but you know what I don't understand? I guess because I'm a science educator, I don't understand people who are not interested in learning. I don't get that. I don't understand a person like that. Okay, who says, I'm just going to switch on the light and go, so what? I switch on the light bulb and I've damn well got to know how come the light came on.
Well, it's funny you say that. I can remember, and I must have been all of about 5 or 6. My parents bought me a transistor radio for Christmas. Within 15 minutes of unwrapping it, I had the thing open and having a look on the inside to see how it worked.
Yeah.
It's that natural curiosity of us being human beings is to know how things work, to see the insides of things. Going back to the Stone Age, the early doctors and that, how did they find out how we worked? By cutting open corpses, by opening up, biology on animals and stuff like that.
Yep.
It's the inquisitive nature of our species to know how things work.
Yeah, that's right.
And to be so disingenuous to say, no, you're all wrong. It's not a matter of, well, explain it to me, show me how. It's just, no, I don't understand, therefore you're wrong.
Yeah.
You know what, Peter, you just reminded me of the fact that when I was that sort of age, my dad wouldn't let me have screwdrivers.
I got mine taken off me. An incident may have occurred with a toaster at one stage in my life that had one of those timers, and I ended up with burnt fingers from the wires on the inside of the toaster, and sitting there with a pale look on my face after getting a jolt from 240 volts. And
you didn't do it to a powered up one.
I would have been 6 at the time. Come on. It was at that stage of my life that my father decided to introduce me to a wonderful man that really shaped my life, called Dick Smith.
Oh yes,
and
beautiful
and
stuff. Yes.
Dick Smith, for the people out in the community that don't know,
they used to have real electronics stored in.
He did this wonderful series called the Dick Smith Funway Electronics for Children.
Yep.
And it started off with basic breadboard electronics, where you'd lay it all out on the breadboard. I started earlier in my life, so we didn't have breadboard. All of mine were actually screwed onto chipboard.
Yeah.
So you'd screw it all down and it would work. I progressed on to the soldering with the PCB boards. And that's where I got my first taste of putting stuff together and learning how stuff works.
Yeah, exactly. Yeah.
And I thank my father for my, for the rest of my life, for showing me that even learning stuff yourself, being open to the idea of reading a book and putting what you read in that book into practice helps you learn. Being open to the idea that you don't know it all. Sometimes you just need to ask someone that I like to call a grey beard, but it's a term of endearment, meaning someone that's older and wiser than yourself, someone that's been around for longer than you, to explain the situation to you. Because quite often the like I said before, the greybeards, they're the ones that already know this stuff. They're the ones that can point you in the right direction. And when you can get to the point of you do something and they'll go, oh, I've never looked at it like that before. That's when you can turn around with that little bit of pride and somewhat subdued ego and say, oh, I've shown him something now. I feel really good. We
can all learn. I learn something every single day.
Yeah, and I think that's the key there, Professor Phil. Every day is just another day to learn something new.
Absolutely. Yep, absolutely. No problems with that. Absolutely. Yeah. So I learned something off a flurfer, to let me tell you. So I'm always struggling with this idea of how to replicate Young's double slit experiment. Because you've got to get the slit, fine enough and close enough together. And this flurfer came up with a brilliant idea of putting 2 razor blades together, really, really close.
Yep.
And then shining the laser through that space in the razor blade and getting the interference pattern on the wall. And I thought that takes a flurfer to think of something like that. That's just brilliant, So now for sure, when I have to demonstrate Young's double slit experiment, I'll get a cork, put 2 razor blades in it really, really close together, and get my laser to make an interference pattern on the wall. Perfect. Now I've just got to find a way to put that in a box so that a whole bunch of students can do it themselves.
Well,
Yeah.
the best thing about using a razor blade is it's a known size, shape, and the quality will be somewhat similar all the way through.
Yeah, for sure. Yeah, so I'm looking forward to that because I've never thought about using the razor blade, and there was some flair for doing it on the screen. Oh wow, this is fantastic. Learned something
Yeah.
from this guy.
You know what's funny? Talking of the double split, the double slit experiment. Um, when I was building a numerical model of wave propagation, um, making it do young slits was one of the requirements I was given
Yeah,
to to show that the model actually did work.
yeah. So how did you get the two slits together? How did you do that?
Oh no, this was a numerical model, so I had to
Okay,
build.
numerical. Okay, so
I
yep.
had to build this. I had to build the slits
Yeah,
into the model because, of course, when you're modeling propagation, you need to model the. It was a case of modeling the environment as
yeah.
that it was propagating through.
So you're looking at path difference.
Yeah.
Yeah. Okay. Yeah. No, that's good.
Uh,
So the hard thing is that you like, for me as a physics educator, I've got to find a way. I always try to find a way of building a physical model to try and demonstrate a concept like that, and trying to build a physical model of the Young's double slit experiment is pretty difficult.
Yeah, I was actually basically building a numerical theoretical model
Yeah.
of acoustic propagation in the North Sea.
Yeah. Excellent. Yeah. So
But
this is radio.
No, this was acoustic. So it was
Acoustic, as
effectively
in just sound. Yeah. Okay.
as in sound. Yeah.
Yeah.
Because obviously that's kind of important with the work they do in the North Sea.
Yeah. Yeah.
You know, being able to have a numerical model of it was of use, which was why it was handed to me.
Yeah. Yeah. Have a look at that. That's a nice graphic there. LED light bulb. Yeah. Yeah. That's really good.
I mean, incandescent bulbs. I wish they hadn't made them completely illegal because they.
They have their uses.
Yeah, I mean, if you want actually something that's pretty dang close to a black body radiator,
yeah.
you want
you could use one of
an
those.
incandescent light bulb.
Yeah, that's right. Yeah, exactly. Yeah, you could. Yeah.
Like I said before, you can even if you push the power up through if you can push the power up through them, you can even move them up to having a.
Doesn't
it? Yeah. That's one of the reasons why those the HID, the high discharge lights are that color, because they are an Exxon, for all intents and purposes. They're a xenon globe. So the light that you're getting is nothing more than the arc of plasma between the two contacts, which is the same as a mercury vapor light.
Well, it's even more efficient than that, and one of the beautiful things about it, because it's xenon, it's a noble gas, which means that it can never react with anything, so it's supposed to be good, long life.
Yeah, no, and well, there's no filament to burn out.
No.
The only thing that does let those down is that the electrodes can slowly deteriorate and be ionized and deposited on the inside of the quartz lens or quartz glass on the inside.
That's that's only because it's impossible to get the kind of purity that you need.
Yeah.
And but if you did spend a lot of money, I'm sure somebody would make one with even.
Well, let's be honest. They're making them in the thousands in either China
right. So
or
it's not worth
Thailand.
it.
You know.
Yeah. You could probably get one to last a few years. So why bother?
Yeah, I mean they last long enough. And anyway, as a manufacturer, you don't want to make something that lasts forever.
Built-in redundancy.
Yeah, you want to have a especially for things like light bulbs. If you're a manufacturer of them, you definitely want them to have a fixed lifespan because hey, you want to keep selling the dang things, don't you?
Yeah, that's right. Well, I'll tell you what. I just not long ago, just a few months ago, one of my lights went out on my Mercedes, and I went back and I said, "Well, what do you can I have one of these?" Thinking I was going to spend about $20. $500.
Yep.
$500. So anyway, I said, no, bugger that. I'm not, you're not going to rip me off like that. So anyway, I managed to get one for $36 on eBay and it works fine.
Yep. And I can remember when I was working at the car repair joint, Professor Phil, even the second-hand market for a lot of these custom lights. And when I'm saying custom lights, I'm not necessarily talking about your Mercedes or your BMWs, but even some of these Toyotas out nowadays, the manufacturers are becoming, I'll use the word sneaky.
Yeah.
And they'll make a special fitting for their special globe that goes in their special light. So they're not interchangeable, which means they can throw the price up on them.
Yeah, no, that's right. Yeah, that's just so wrong, isn't it? Yeah, it's just that's so.
I can think of another company that has got that process down to a T.
Mm.
Yeah. A fruit beginning with the name a fruit beginning with the letter A.
Yeah, apple. Yep. Yeah. Yeah. I tell you what, there's something to be said for the old Kingswood. If it didn't fit, you'd surely find something that did.
Yep.
If the original part didn't fit, or you could just make it fit.
You Professor Phil, on the steering linkage that goes from the firewall to the steering box, the steering shaft that's on that section, and on the end of your steering column where it joins onto, there's a concertinaed rubber section in that area.
Yeah, that's right. Yeah, I know what you're talking about. Yeah.
Yeah, well, you could go and buy that, but I wasn't able to get one at the time, so I pinched a bit off a funnel.
Yeah.
The concertinaed bit off of just a normal funnel, and I whacked, and it fitted on perfect, and it's still there today.
Yeah, no, perfect. That's a beaut thing
about it.
It
does the same job. It protects the knuckle and everything.
Yeah. No, that's perfect. I remember getting stuck once with a distributor cap and looked around, found an old fag box, cigarette box. Remember they used to have silver paper in it?
Yeah, that's good for fuses too.
Yeah, so pulled the silver paper out and put it up near the button and worked perfectly.
Yeah.
We all know about
days, Oh, I haven't seen have you seen a strobe light recently?
I've got a timing light I use
That's
on
what
my
I mean,
car.
Yeah, timing light.
I use that on the wagon when I do the timing.
Do you need one, Professor Phil?
No. I open up the Mercedes. I wouldn't even know where the bloody thing is anymore.
No, you don't hook it up to your Mercedes. All you do with your Mercedes is you plug it into the computer.
Yeah. No, I had somebody come around and do that and do some timing, and I thought, gee whiz, you charged me $300, and all you did was spend 5 minutes looking at a computer.
Yep. Yeah.
So where do you buy this bloody computer from? This software?
Well, they're not that expensive, actually.
Yeah, you can get small versions nowadays.
There you go. The standard set of fuses.
Oh, wow.
I like the audio visual fuse. That's my favourite.
Yeah, the audio visual fuse is good if you dare use one.
I'll be honest.
Now they're coming too. And now they come in two sizes. They come in big and loud and small and not quite so loud.
I'll be honest. There, I did have a car.
I love those fuses. Yeah.
I did have an old HX there for a while. That its fuse box was a magazine full of 22 long rounds.
Yeah.
They fitted perfectly, and they got me home.
Oh God, that bullet reminds me of a time when I managed to steal one from my dad and was just holding it with a pair of pliers and using a nail on the other side to hit the firing pin. Oh my God, I just
How
cringe at some of the things you do when you're a kid.
How long were you deaf for?
The bloody thing didn't go off then, thankfully.
Well,
it didn't go off. So I took the insides of it out of it and put it in a key. And this is how I blew my hand apart, because I put a nail in the key and hit the nail.
Oh.
So I did the damage anyway, but at least I didn't. The bullet could have done a lot more. Could have hit, my brother or something like that. He was standing nearby. Thank God it didn't happen.
Fortunately, if you actually think about the physics of it, the bullet, when you do it and it's not contained in a firearm, the bullet doesn't actually really try and go anywhere.
No, it's the shell it does.
It'll just explode.
It's the case. No, it's the case that tries to go somewhere.
Yeah.
Because it's got the less mass, and also once it's separated the bullet from the case, all the propellant is still inside the case, and it just becomes a little miniature rocket engine.
Yeah, true, exactly. It would too. And when you think about it, it's if you look at MV1 equals M1V1 equals M2V2, you're quite right. It's the case that would keep going, not the bullet.
So I'll tell you a lovely story. We were home on school holidays when all young boys got up to mischief and untoward.
Usual time, yeah.
Yeah, and I came around the corner, and here's my little brother sitting in front of Dad's shed with a claw hammer in his hand, for all intents and purposes, just hitting the claw hammer, in a nail in action, into the ground.
Yeah.
And I asked, "What are you doing?" And he goes, "Like they did on the Bugs Bunny cartoon, I'm hammering a bullet into the ground."
Okay. Oh no.
And as I reached down to grab the hammer off him, he was a few years younger than me.
Yeah.
It was the final blow that actually made because he had, if you can imagine this, nailed the bullet into the ground, bullet first, or round first.
Yeah.
And hit the primer at the right way, and it went bang. And I don't think I could hear properly for about 2 days. I was literally arm's length away from this thing going off. No barrel, no rifle, nothing stopping the sound from coming out. Got covered with dirt and bits of debris that flew everywhere.
Yeah.
Both of us were fine because, well, obviously the projectile went straight into the ground.
Yeah.
There was bits of brass from the shell going everywhere.
Yeah.
Nothing majorly, thank God, happened.
How lucky are you?
No blood or anything like that. We were just so lucky.
You could have been hit in the eye. You could have been hit in the temple. There's so many thousands of ways that you could have been permanently injured.
Oh, for sure. And like looking back, you look back and think, oh, how dangerous was that? I couldn't hear properly for a couple of days, so obviously I did some hearing damage then.
Yeah.
Yet, it's good to giggle about it now and tell kids, don't do that. It was silly.
Yeah, right.
Yeah, I just remembered that one as well.
Oh, well, I'm going to go and get a sandwich, guys. I'll be back in a few minutes.
All right, Professor Phil.
Good morning, everyone.
Yeah, casual.
Hello, casual.
Did you finally pinch the computer off your daughter?
Yeah, I got it back, yeah.
Once you get up to go out of the room, and then you go, and then you dived on it.
No, she was going out anyway, so she was just doing a bit of schoolwork on it, so she's staying with me for a week or so. So.
Oh, okay.
Oh, rubbish! You went to the fuse box and turned the power off. I know.
Yeah. There was one thing. There was one thing missing from that picture, Alan. The paper clip.
The fuses?
The paper
clip. Yeah, the paper clip. That's got to be at least worth a £5, hasn't it? Maybe a bit more.
I've always thought that cigarette foil was best because at least it burned through if you got an electrical problem.
Yeah, and when it started heating up, it gave off that waft of burning paper.
Yeah, then you just screw it around again and shove it back in again to keep going.
That's right.
I think that little tiny nail, I think, what was it, a 12 amp? I think that's a bit overrated, to be honest. It would have been underrated. I would have think it would have been a lot more than that, I think.
No, it's...
that little tiny nail.
The little tiny nail is about 100 amp.
Yeah, I was going to say, yeah.
You got the nail. The little nail was 100. The scratched up silver foil is 250. 350 for the 762 by 51 NATO. 600 amp for the big nail. 1500 amp slow blow for the bolt. 2000 amp slow blow for the spanner. Or 130 amp on the ring pull, but we don't get ring pulls like that anymore. And 16 amp.
No, we don't.
And 16 amp for the Dairy cheese wedge.
Yep.
Although I think that's the laughing cow one instead.
Oh, sorry.
Milk two sugars, Terry.
Yeah.
Milk 2 sugars.
Yeah, okay. What I was saying about the foil thing, I learnt that when I was about 15 to use it as a fuse because I was explained, which I still remember, is the reason that he used the bit of foil. He said, well, if you've got an electrical problem, the foil will burn away because if your fuse blew, you've got a problem.
Yeah.
There we go.
That's and then all through my young childhood, any time my mates had blown fuses in the car, I'd say, oh, you got a cigarette packet? Yeah, and I fixed it for him.
It's even got the ladybird on it. They even got the ladybird on it too, Alan.
I know.
It's awesome.
I actually acquired that with a different trade on it, but Photoshop and everything. I managed to correct the trade on it.
I like the British military uniform guy sitting there as well, praising it.
Yeah. Oh, you'll notice there's military from all of the ages and all of the.
Yeah. Oh, yeah. Look a bit closer.
Hey, Casual, you missed out on a spacewalk thing tonight, this morning, today.
Yeah, there was another EVA. Yeah, you're right. Yeah. No, I stopped doing those because it drags on a bit and people kind of lose interest and stuff like that as well. So, it does go on for quite a while. I mean, you don't always know what's going on. So, it'd be nice if NASA could sort of put something up the screen. What they're actually doing at that moment in time. But it's a.
Well, unless you want to go back to Flirt stuff like the Nathan Thompson saga, where somebody with the Nathan Thompson crowd put a video out to say we didn't meet the challenge.
Was there a time limit on that? Was there?
No, it was the terminologies of the experiment showing that we solved his flat Earth request thing.
Yeah.
They picked on it and said, "No, we didn't do it right."
Was this a response to Simon Dan's one?
Yeah, it was a response to the Simon Dan one. Yeah.
I mean, of course.
I mean, of course he's going to say that. Of course he is.
My only question is can you hold their feet to the fire, and say, right, well, let's get this written out. Write out your stipulations. Make it a formal contract. Make it real. Let's do this.
Although, yeah, but they'll still wiggle out of it. There's no way they're going to admit that you've done it right and you've proven it, are they?
If we finish with the sun tonight, we can go on to part next time.
Rockets.
Yeah, I think we should.
So.
Yeah, I think we'll go to part 2, Peter, next time. So we're finished with the sun in the chat. So it's a free for all now, by the sound of it.
A free for all. So, how do you want to do this, Terry? Do you want to let the chat tell you what you're doing next, or are you going?
Well, I was just going to start watching some videos, a bit of entertainment. Hey, Glaby.
Hello.
Where's your avatar, Glaby?
I don't know. I signed in through the like the way I normally do, and it didn't come up again. I'll have to try and work it out.
We'll have to beat it up.
Gee, these old people that don't know how to do things.
Oh. It's ever since I had to reset my computer. I've had that problem.
Anyway, where was I?
So I can delete sunshine out of my YouTube search then.
Yeah.
Type back, and put flat Earth back in there.
Yeah. Oh, I'm going to find that video that I was talking about. If this is the one I was talking about. Davros put it in earlier.
Yes, you did. Have you got it, or do you want me to bring it over?
Flat Earth Millionaire, he's got a challenge out for all the Globers to prove we live on a spinning ball.
The challenge, there's 3 main parts. We want to see replication using the scientific method, observing, measuring, and repeating water sticking to a ball. It doesn't even have to be spinning. We just want to see water conforming to the exterior of a ball.
Hi. Good afternoon, YouTube. Just want to make a quick video in response to Sawman Dan claiming that he met my 3 challenges. He starts off in the very beginning of showing a ball with water falling off the bottom. And I clearly stated in my challenge, I want to see water sticking to a ball, to the exterior of a ball, without it falling off the bottom.
No, you didn't say that bit.
We just want to see water conforming to the exterior of a ball.
So right there alone, that one point you failed miserably. But yet all your followers, all your religious, zealous cultists.
I do have a way of solving that problem with the water sticking, water sticking to a ball, but not falling off the bottom, just to shut them up.
Think that you won. I mean, I'll give you props. You are definitely a good brainwasher. You are a great mind controller. I'll give you props on that. It just goes to show that the average globetard is easily hypnotized. So just wanted to address that real quick. I'm going to address the other 2 points where you absolutely failed miserably, Sawman Dan. So anyways, just wanted to touch base on that real quick. Sawman Dan, you're an idiot, dude. And it's amazing how all of your ignorant, globe-tard, peasant followers fell for it. I clearly stated that you cannot have water sticking to the surface of a ball without it falling off the bottom.
No, he didn't say that bit. He did not say that last bit.
For all the Globers to prove we live on a spinning ball.
The challenge, there's 3 main parts. We want to see replication using the scientific method, observing, measuring, and repeating water sticking to a ball. It doesn't even have to be spinning. We just want to see water
to do with the water dripping off the bottom.
Conforming to the exterior of a ball. Gravity.
So hang on. If you get a bubble, could you classify that as a ball of air?
Technically, yes, but I think they want something solid.
No, I can solve the water sticking to a ball problem. That's easy.
Well, I had a theory there, Terry, and
without
I'll see
it
how
dripping
close.
without it dripping off, and it
Yeah,
could be
so
and it could be rotating around, or it could be still. It wouldn't matter the difference.
well, I had this thought where we get a high precision set of scales, measure a tennis ball before you wet it, put your couple of drips of water on a tennis ball, measure it afterwards, show that it's heavier, and nothing's going to drip off.
But they'll say that's because it's slightly fluffy, and the fluff is holding the water on by.
I can do it to a smooth ball.
The problem.
It's all right. M-Ball said the same as I did, but obviously just before I did say it in the chat.
Sorry,
no, you can't use ice because that's a different that's a different element. Ice.
An ice ball.
Yeah.
That's awesome.
The thing is that we absolutely know for certain that you would not be able to do his challenge as he has put it because he has set an impossible task.
I can do it. I keep telling you. I can get water to stick to a ball.
Tell us, Terry.
Show us.
Jeez, I've been trying
to
citation
I've
needed.
been trying to tell them that I could do this before, and no one's listened.
Go, Terry. I'm listening.
Did he actually stipulate the consistency of what water is?
No.
So in other words, you can raise the consistency of water to another level, where it's a little bit more viscous, like an oil, or even thicker.
Yeah.
So it'll still be water.
But
he never stipulated what type of water, because water can still be more viscous in some way.
Yeah, well, so on that premise alone, you could put a marble in an ice cube tray, freeze the water around the marble, and there you've done it.
Nah, the water's frozen. You can't. You'd have to use actual liquid water.
Well, does he say liquid water?
If it was liquid, it will eventually fall off, thanks to the fact that we're next to this huge, great big mass that's going to skew the experiment.
Yeah, but I was going to use a gelatin type liquid, like water more gelatin like.
Yeah,
so
that's
that
not
way
pure water.
Yeah, but they can't tell the difference by looking at it.
Like what was said to me once upon a time. You get your basket. Oh, excuse me. Get your basketball. You get a sponge. You wet your sponge. You wipe the ball. The ball is then wet. The water's not falling off. Job's done.
Who was it said that to scale you would just need a basketball and a teaspoon of water or something?
It's not even not even a teaspoon. I think it's for a standard basketball. I think it's.
You got the image?
Yeah, just give me a moment.
Someone had said it before. I can't remember who it was. Was it you? Maybe it was.
It probably was me.
I'll be back. I'm just going to try and fix my avatar.
Yeah, that's fine.
I might be long.
Take your time.
Okay.
So.
Hey, we had two casual spacemen then.
That's very casual.
I just noticed that. I just caught a glimpse.
I see casual spaceman talking, and I'm going, what? That was Glaby.
I wonder who that is.
Yeah, Glaby would have done it. Yeah.
It calls us Glaby. I recognise the voice as well.
Yeah.
Yeah, where is it? I've got it here somewhere, Pip. Oh, there it is.
I might get a copy of that too and put it in my science pictures folder.
Yep. All right, Terry.
Not now. You can give it to me now.
Yeah, no.
Or you can post it in somewhere in Discord, whatever.
Yeah,
I'm waiting for Professor Phil to come back because I wanna show him some.
Oh, I've got DMs. Oh, look at all these DMs I get. I keep forgetting to answer to people.
Yeah, let me just fix this and zoom it in a bit. Oh, stuffing things, Terry.
Well, it's very small. Can I do
Pinch out. Oh, yeah.
Yeah, Bohobo just mentioned the same thing as I just did, casual, about the live.
I'm sorry, you can't read the writing at the bottom, but you get the idea.
We've got Big Blue here now.
Wonderful.
Now things are going to get rolling.
And above.
So yeah, so that big drop of water is the salt water on the Earth, and that small drop of water, that would be the fresh water on the Earth.
Yeah.
What,
In
even the
relative,
ice?
in
all the
relative,
ice?
yeah, in relative comparison to the Earth itself.
Mm.
No, just liquid water.
Yeah,
Terry.
yeah.
Yeah.
Yeah, but there's two bubbles. One's
Yeah,
water
so
and one's the other.
the big ones are salt water, and the little ones are fresh water, Terry.
Right.
It must be all the water because we've not got any ice caps on the globe left, so they must be using all the
true.
water.
Oh, the ISS is doing something exactly what we were talking about tonight, by the sound of it.
What do you mean?
Well, it's better known as the Alpha Magnetic Spectrometer.
Yeah, they're still fixing that.
Yeah, that's.
Well, I mean, they've done most of it. They're just doing the last bits now. They probably
Yeah,
got
I think we've
a couple more
probably
spacewalks after this.
most of it. I got this message about an hour ago.
So
Yeah.
I think it was me and Demonic sat down and did the calculations. We worked out for a standard, the standard game basketball, you would only need 4 mils of water to represent those two drips. So you're literally wiping the whole basketball with the water. It's such a small amount in comparison to the rock mass of the Earth.
Yeah.
You know, but
Yeah, Professor Phil says any ball that is weighed all over scale to the size of the Earth would have more water than all the oceans.
And so they get hung up with that magical 72%. But what they don't understand is that 72% is covering the
surface,
surface,
just the surface
of the Earth. It's not the whole Earth.
Yeah.
It's not 72% of the Earth's mass or anything like that.
No.
You know,
they're idiots.
I've heard that all the time. I've had arguments of people saying, "Oh, the Earth is made up of 72% water." No, it's not. It's covered up 72% of the surface. In other words, 72% is what we can actually see is water. If you look down on the Earth, it doesn't mean that 72% of the Earth is made up of water. Oh no, it's not. It's 72. No.
I'd just like to know let you know that Blue's here.
Hello, Blue.
I think he's here.
He's here, but he's
I did
muted.
notice.
He's muted.
Sam Cam says, send him Dale's water.
Oh, and a casual spaceman just joined.
And he still hasn't. He still hasn't.
I'm the casual spaceman.
No, this is the casual spaceman because that's what it says.
No, I'm the casual spaceman.
I'm the casual. Wait a minute. I'm the casual spaceman. I'm the casual spaceman shrink.
Hi.
Hi, Blue.
Hi, Blue.
I am not the casual spaceman.
No bleep, Dr. Sherlock.
And you didn't connect your Zoom thing to your Google thing somehow.
Oh no, I signed in through Google, and it won't bring up my avatar for some reason.
Did you go into the settings in Zoom and actually tell it what avatar you want? No. No.
Probably not.
Or did you click the link or copy and paste the link?
No, he's still got to go into Zoom and tell it what one he wants.
It's probably lost his old avatar. That's the problem.
Yeah. Go back into Zoom and look into the settings, and you'll find your profile, and it'll fix up your avatar in there.
Okay.
What do we got here? Who's sharing?
Yeah, Blue helped me with this little. Hold on.
You needed help. You needed help.
No, we can hear you.
Oh, you can hear me. That's right. I thought I was muted for a second.
Did you need help?
Yeah, I had a bit of a spat with a guy that was claiming that rocket engines don't work in a vacuum. So what I did was I provided a whole load of links explaining all kinds of stuff, how engines work, how they work in a vacuum, the fuels, and all sorts of different things. Went on and on and on and on. All these.
Or how a rocket works.
Yeah. How rocket engine works and how it works in a vacuum. This is his argument. Rockets can't work in a vacuum because it hasn't got anything to push against.
Off. Yeah, I know the argument.
Yeah, exactly. This old argument, right? So I finished with this, which is a statement that Blue helped me with the other day. So I said, a rocket engine in its simple form creates a gas pressure by burning the fuel and oxidizer in the combustion chamber and then pushes the mass of the combustion gas out the nozzle or bell as it expands. Expelling the mass of combustion gas results in a force in the opposite direction that propels the rocket forward. So this applies to Newton's third law of motion. For every action, there's an equal and opposite reaction. So no atmospheric pressure required. So what have I got? As I said before, I can do this all day long and twice on Sundays. You can deny it all day long, but it will change the damn thing. So go ahead and deny science. So he responded with this gibberish. I mean, after he looked at he's supposed to have looked at all the links that I provided. Of course, he bloody didn't. If he had, he wouldn't have said this. A rocket obviously needs to take its own air and fuel mix. That's why it's a rocket and not a jet engine.
Duh.
What?
The vacuum chamber is not a vacuum. I never mentioned anything about a vacuum chamber. As soon as the rocket propellant is fired, the vacuum is lost. It is not even a proper vacuum anyway because the pumps were too weak.
What?
A rocket engine in its simple form creates a gas pressure. Your words. Why don't you run along and tell your professor friend how you can create a pressure in a vacuum? Remember, this whole credibility is in the line. If it's not answered the question correctly, it is impossible to create pressure in or near a vacuum. Creating pressure is Newton's third law, apparently. The action of expanding rocket gases. Yeah. Into the resistance of the atmosphere, create a reaction of increased pressure.
I didn't know NASA had a bullshit generator.
I know, that's what I was kind of thinking when I was reading it.
Well, if they do, the friggin' thing is broke. Because this one,
yeah, exactly.
This is not even good bullshit.
I know, it's terrible bullshit, isn't it? So yeah, after a sort of I mocked him a little bit and then blocked him because I was just getting bored. He was just
Yes. So he's talking about setting off a rocket in a vacuum chamber, like the big one that NASA have used in the past, the one that they used to drop the bowling ball and the feather in.
Yeah.
Quite possibly, yeah. I'm not quite sure what he's talking about.
But realistically, you wouldn't. That's not something you would do. You wouldn't.
I think
Sorry,
you know what I think he's talking about, and I've seen a couple of videos where guys have tried to construct a little vacuum chamber, homemade type, and then light a little tiny one of those little package rocket motors in it.
Yep.
Yeah, a little solid propellant.
Yeah. I think that's what this idiot's talking about.
But the thing is obviously he doesn't realise that yes, the rocket fuel itself, particularly on those solid fuel, it's a fuel mixed with an oxidizing agent. With the liquid or even the hybrid rockets, the liquid is generally the oxidizing agent with a fuel agent as well. So yes, it is taking oxygen in the oxidizing agent and the fuel. There you go, not a problem. And as for the expansion of the thrust coming out of the nozzle, well, geez, if you really wanted to get anal, the first time the rocket goes bang and the stuff starts coming out, there's stuff there in the vacuum there. So there you go. There's something for your rocket to push off. You know, like you don't need it though, because the motion of the stuff moving. It's like the old experiment that you do at high school where you sit on a skateboard and you throw like a tennis ball backwards, or you throw a medicine ball backwards. You know,
exactly.
The action of throwing that away from you actually propels you forward.
Sure.
You know, that's it.
It's almost as if forces suddenly cease to exist in the vacuum of space.
Yeah.
It's almost like they disappear automatically as soon as they hit the Kármán line. Oh, forces stop. That's it. That's pretty much what he's pretty much saying. You know?
Physics stop here. No physics go past here.
Oh, Jesus
Yeah, exactly.
Christ.
Go on, Blue.
You could set a guy on the engine bell and have him lock his legs around it and throw tangerines off the back of the damn thing, and it would propel itself forward. I'm sorry.
all of a sudden, I'm seeing NASA.
Genius.
I'm seeing NASA with their new rocket. I mean, their new satellite up in space, firing tangerines to get it to orbit.
Yeah, that's right. Yeah.
It's got like a. It's got like a.
raining oranges. We know why.
It's got a. It's
You know
got
how
like a
fond old boy was of
potato.
tangerines.
It's got an automatic loading tangerine cannon that fires tangerines to put it back onto orbit.
Yeah, NASA or Big Blue's inventing a new rocket fuel, tangerines.
We're 32 tangerines off orbit.
Oh yeah, but what are you going to fuel the tangerines with? That's kind of important to know what you're going to fuel the tangerines with.
Oh dear. Now, I can remember, like, back when, I'm going back a little ways here, but back when Buck Rogers was you know, the classic 70s space TV show.
Yeah.
And
Buck Rogers in the 25th century.
yeah,
wasn't
yeah,
it?
yeah. And
That's the one.
Hold on.
you know, they were out in space. They were out in space, and they were literally using aerosol cans to move themselves around in space. And in reality, that would work.
Yeah.
You know,
Of course.
it's all about releasing pressure in one direction to give you thrust in the opposite direction.
Well, yeah, it's really about moving mass.
Yeah.
If you accelerate mass, there's a force required.
Yeah, well, in that movie Wall-E, he got a fire extinguisher and he was spraying himself around space.
Wall-E.
Well,
Hey, I tried that one time on a skateboard, and I will tell you right now, it works.
It works.
Long enough to bust your ass.
Don't do it on a computer chair. You have no control.
You don't have any on a skateboard
I've seen that.
either, believe me.
And then this dimwit, and then this dimwit for the. Oh, sorry, Terry.
No, that's okay, Casual.
I was apologising to Alan, actually, not you, Terry. I meant. And then this dimwit finishes with this as well. I do this all day long, literally spending my time explaining to people how they've been fooled all day. Yeah, okay.
I swear to God, we need to start a GoFundMe and actually put them all up in space.
Yeah, I'm ashamed to say the guy's a Brit as well. He lives on the Isle of Wight.
Good grief.
Yeah, afraid so. He's English and he lives on the Isle of Wight. Well, people on the Isle of Wight are a bit weird.
Yeah.
Yeah, anyone from
Gary
over
Isle of Wight. No offence taken.
Yeah.
I thought anyone from over there.
Gary's one of the better ones.
Yeah, he's one of the better ones. Yeah.
I thought you were all a bit loopy over there.
Yeah.
Kiss me.
No worse than Australian.
How dare you?
Nope.
How dare you?
Time for Alan to take his pills.
Yeah.
Take your pills, Alan.
Yeah, it's drug time.
Alan.
Steve.
Alan,
Steve.
and just to save any, is Alan still there or is he gone?
I see.
No, I'm still here.
Well, just to save you having any accidents with the pills, just use a funnel.
I'm back again.
Yeah.
Welcome back, Phil.
Welcome back, Phil.
Oh, thank
Oh,
you.
Phil's back
you
with
missed,
his
you missed,
What have you been talking about?
sandwiches. What did you have?
Oh, I've got some croissants with cheese.
We were discussing
I'll share my.
Absolutely no food for me, but there you go.
Is the screen free? Because I'm not in the lounge room at the moment.
Oh, that's a
it's
nice
still
picture
free.
of the
Yeah.
model. Yeah.
We were
Okay,
discussing.
so what's the topic?
We were discussing.
We were
the
discussing
virtues of-
Tangerines.
Tangerines.
Tangerines. It's the new space
Yeah.
fuel of the future.
Oh, okay.
Yeah, rocket fuel.
Oh well, you know the skin out the stuff that you get in oranges. There's an oil in it which is very very flammable.
Well, we were just going to fire the tangerines out of like a potato gun or a lemon cannon
Okay.
And,
so,
and
as a new propellant for a rocket in
so
a
that
vacuum.
so that we can use that to put the satellites back into the correct orbit.
Oh, right. Okay. Well, Newton's third law, that should work.
Yep.
Yeah.
Oh, funny you should say that.
Yeah,
Professor.
funny you should say Newton's third law.
I'm glad you asked.
Glad you asked, yeah. Yeah, here we go. I was waiting for this.
Right, I was just explaining to the guys, and Big Blue got a big kick out of this as well. Is on one of my videos, I had a guy making a claim that a lot of flubs make is that a rocket can't work in a vacuum because it's got nothing to push against. You know, that old argument.
Well, would it need it?
Yeah. So I had a bit of a spat with him, and then what I did, I provided a whole load of links of explaining all stuff about rocket engines, how they work, and the fuels, and all kinds of things. And eventually, I don't know. There's one comment that's actually missing, but he said that he looked at all the links and he just thought they're all nonsense, right? So one of the statements I finished with after I finished with the links, I said, and Big Blue actually helped me with the wording of the statement to make sure I got it correct, and he kind of expanded on it a little bit. So just to explain it, I said a rocket engine in its simple form creates a gas pressure by burning the fuel and oxidizer in the combustion chamber.
Yeah.
And then pushes that mass of combustion gas out the bell or nozzle as it expands.
Mm-hmm.
Expanding the mass of combustion gas results in a force in the opposite direction that propels the rocket forward.
Yep.
So this applies to Newton's third law of motion. For every action, there is an equal and opposite reaction.
Yep.
So no atmospheric pressure required to work. Yep. So I said, what have you got? As I said before, I could do all this all day, blah, blah, blah. So he replied with this.
Perfect.
I don't know if you can see the screen. Can you see the screen, Professor Phil?
Yeah, I can.
So he replied with this.
I've looked at your links.
A rocket obviously needs its own air and fuel mix. That's why it's a rocket and not a jet engine.
Okay.
The vacuum chamber is not a vacuum. As soon as the rocket propellant is fired, the vacuum is lost. It was not even a proper vacuum anyway because the pumps were too weak. A rocket engine, he quoted me, a rocket engine, its simple form creates a gas pressure. Your words. Why don't you run along and tell your professor friend, because I mentioned you before,
okay,
can you create a pressure in a vacuum? Remember, his whole credibility is in the line if he does not answer the question correctly. It is impossible to create pressure in or near a vacuum. Creating a pressure is Newton's third law. The action of expanding rocket gases into the resistance of the atmosphere creates the reaction of increased pressure.
Oh, okay.
Yeah.
Sure
I just wonder what you think of that.
Well, it's all nonsense anyway, but
yeah.
I'm just trying to think of a way to that you would answer this so that it becomes obvious even to this person. Your description of the rocket, by the way, is perfect. That's exactly what happens. So I'm not sure why. I can't see how he's even in his comment. He's not even contradicting what you're saying anyway, except to say that he. I can't see any contradiction with what you said anyway.
No.
Simple gas. It says here, a rocket engine is in its simple form creates a gas pressure.
Well, he's quoted me there.
Yeah,
he's quoted me. Yeah.
How can you create a pressure in a vacuum? Well, why are you creating a pressure in a vacuum? It's precisely what you said. You're creating a force with the gas on one side and creates an equal force on the other side. It's how hard can that be?
Well, this is the bit where he says, in the vacuum of space, there is no reaction until the rocket gases hit something with mass.
No.
So there's this thing. No, exactly. The rocket gases cannot hit the rocket combustion chamber walls because the vacuum is the lowest pressure side and the rocket gases always go to the lowest pressure first. Gibberish.
Yeah,
high pressure always go to low pressure, just as hot always goes to cold.
Yeah, well, it's, it totally is irrelevant to any of that. And it's, as you describe it adequately, I mean, I think about asking somebody like that, if I had if I had a vacuum and I had, let's say, an explosive, would it explode? Would a bomb explode in a vacuum? There's the question. Well, if it would, then what did it have to push against? I mean, that's all it is. That's all a rocket is, a controlled explosion.
Yeah.
The bomb with a hole in the end of it.
It's funny you say that, Professor Phil. When I was with the Defence Force and that, I was with the engineers. I spent some time during the Olympics with the disposal team for the Olympics, and one of the ways that we actually dispose of the larger size ammunitions from planes and stuff like that is we use a shape charge to pierce a hole at both ends of the ammunition. And by doing this, it actually ignites the fuel that's inside, being the explosive. However, because you've ignited it rather than exploded it, as it would be, the bomb itself, the bomb itself will become a self-venting tube. So if you put two holes at either end, it will suck the air in from one end and blow it out the other end, very much like your fire does in your house. So you put your firewood in, you light your fire, and the smoke goes up the chimney. So it's the same thing when they're getting rid of these large ammunitions. They just burn the fuel, the explosive, in a controlled manner, and this stops it from exploding. And like even your plastic explosive, you can actually light plastic explosive with a lighter so that it's burning, and it won't explode. It's quite safe. It will burn controllably, and it's the same in the rockets. Unless everything's been combined in the right formula, it won't explode with a whole heap of thrust. It will just burn, or out in space, it will do not much of anything.
Well, when you ignite both ends of it like that, you're not sucking any air in. The oxidizer is in there; it's already there. It's like any kind of ammunition. Apparently, this guy never heard of the underwater demolition team. I mean, you can blow up any of that shit underwater.
Yep.
It doesn't need oxygen. It's not taking anything in and putting a hole in both ends of it. That's exactly what you are doing is stopping it from becoming a rocket.
Yes.
It'll force it in opposite directions, and it'll just the combustion will stay in one spot.
Yeah. So one of our biggest things that we have to think about when designing a rocket engine is how fast we can burn the oxidizer and fuel. The faster we can burn the oxidizer and fuel, the better efficiency we're going to get from the rocket. And also, obviously, taking the nozzle shape into account. That nozzle shape isn't by accident the way it is. It is very, very meticulously designed for a particular type of rocket with a particular type of fuel and oxidizer and thrust. So this is very highly machine designed, again, for this controlled explosion. I mean, one way they can just look at it and ask them, how do they think a bazooka works? What is the missile in a bazooka pushing against?
Air. Oh, they'll say air.
Yeah, they think it pushes against air.
I mean, how stupid is that? How could they think that would be able to get the velocity on one side if it was just pushing against the air? I mean, that is just dumb.
It's funny you say that.
Well, it frightens the air. That's what it does. It scares the air.
It pushes it out of the way.
Yeah. That big flame coming out frightens the air, and the air slaps at it and makes it go forward.
Because it's dirty air.
Bloody
dirty air.
Professor Phil, can you explain in layman's terms why is the bell of a vacuum engine bigger than a sea level type engine?
That's a good question. Well,
yeah.
Look from a rocket point of view, there's an optimum size of the bell shape. There's an optimum size of that for a particular amount of thrust that you have. So
it's all to do amount of thrust. Okay, right.
yeah. So it's completely related to the amount of thrust that to get the actual optimum size that will give you, just because if it's too large, the energy will escape from it, and if it's too narrow, it won't be. You won't get sufficient energy to the explosion won't be sufficiently controlled. So you getting exactly the right bell shape is quite an art. It's quite not an art, a science.
So that would fit really with the case that it's easier to you don't need as much thrust in a vacuum of space than you do at sea level, because obviously you're fighting against gravity anyway. So yeah,
it's
so
just really in space. Every satellite's built in with many thrusters. Okay, and they have little gas, tiny little gas tanks, and it only takes a puff to move. To move a satellite. So in other words, it's Newton's third law. As you release the gas, you're causing force in one direction and an equal amount of force in the other direction. So therefore the satellite moves because there's nothing to stop it from moving.
Yeah, absolutely. Yeah.
And really that's all it is. It's I don't know why it seems to be rocket, or it is kind of rocket science. There you go.
You would think anybody that's ever picked up a garden sprayer would understand this concept.
Yeah. I mean, how's that? Yeah, just pick up a hose.
Yeah.
Yeah. Pull the trigger on your garden sprayer and feel it.
No, that's right. That'll do it.
Is that water pushing against the air?
Yeah.
Do you feel more push if you get closer to a wall? Come on.
Nope.
I think really close.
Wolfie said the same thing. Wolfie 2020 was in Discord the other day, and he said the same thing. He said that if I put my my engines in my aircraft up against a wall, is it producing more thrust? So, no. So it applies exactly the same thing at sea level than it does, even in the back.
Yeah.
It is. He's not going to get more thrust. Of course he isn't.
Nope.
And he won't.
I remember.
Maybe you should put a challenge out to flurfers. Is actually try and demonstrate if you can actually get more thrust with something up against a wall and not up against a wall. Demonstrate it.
I would have thought by now the flurfers would have been debunked for them. They would have given that one up.
No, they're not.
Oh.
Or are they just new flurfers who don't know who don't know where they're up to?
Yeah. Well, it's new flurfers come along and parroting what the old flurfers have been saying. They're just repeating the same stuff that they were repeating. So
okay,
yeah,
they're trying to get. So they go back to Dubé's original stuff and start and then flurf from there.
Yeah,
and then we just give them the same answers.
They don't know
all
the stuff that's happened in between.
Yeah.
Okay, so, and of course they're not going to watch debunking videos because that would hurt too much.
Yeah, I mean, it's like Red's Reddit was saying not all that long ago. I remember him saying is that he's seeing a new generation of flurfs coming through, but they're saying exactly the same stuff as the ones that were saying a few years ago.
Yeah,
because Red's Reddit, I mean, he's one that's been around for a while.
Yeah,
and he's seen the same stuff being repeated that he's debunked, a few years back.
Yeah. What about the age of them? Is that changing? Do you know? Because it used to be they were sort of over 50 and usually men.
Don't know. It seems to be a mixture to me, from what I can tell.
Because it'd be really surprising to see young people being flurfers.
Well, there seems to be a lot in their 30s.
Yeah. Don't know. I'm seeing older ones and young, because you can't always tell as well, because obviously you don't always see their face either, do you? So it's not always easy.
No. And even being able to see their face doesn't make much of a difference. I mean, look at the age of look at how old Furball is, and then look at how old he looks.
Yeah, he looks about 12, but I know he's.
Rosie asked me when I was talking to her. Rosie asked me why I was talking to a 12-year-old.
I did run up against a new one last night though.
Okay.
That I haven't heard before. Flat Earth Data. You guys know who Flat Earth Data is? He's one of the idiot trolls that wanders around from time to time.
I think I've met him when I was doing Jose's after shows.
Yeah, he used to come on. And,
yeah.
I think Jose finally got enough of him and banned him.
Sorry, Blue.
I said I think Jose finally got enough and banned him.
Yeah, he's debated Team Skeptic, I think, before.
Yeah, I think he got his ass handed to him by a skeptic a time or two.
Yeah, he has.
Well, anyway, this nitwit, this is a new clever one that I haven't seen before. He goes and takes Mick West's Metabunk calculator. He sticks in a viewer height of 1 foot and reads the unrefracted horizon distance as 1.22 miles. Okay. Well, all right. That's what it is. Then he turns around and says, well, that's just built into the calculator, and it's all to do with the Rayleigh criterion and your eye's resolution. That's what stops you from seeing the horizon any further than what it is. Have you guys ever heard of anything like that? Yeah. If you look at the Rayleigh criterion, of course, there's that 1.22 factor in there, and he has no idea what that factor is. But he's now pronouncing that we're just tricking them with our Earth curve calculators and the horizon distance. It's actually just the resolution of your eye that stops you from that causes the horizon to be where it is.
Well,
I've never heard
give him
such.
some. Yeah, I was just saying, give him some credit. At least it's new. Sorry, Terry. Sorry, Alan. Go ahead.
I'm pretty certain now that it was this flat thingy data that prompted this response.
Are you talking to retard?
Oh, was it? All right.
Funny thing, my wife says exactly the same thing.
I think that's actually who I was talking to at the time when Rosie came in and asked me that question.
Well, the Rayleigh criterion simply defines the minimum angular size an object can be before you can no longer resolve it. You can still see it, but two objects will simply become one object at some very small angular size. Yeah. And 1.22 it actually has to do with the first dark ring around an Aries disk. I don't know where this guy gets this shit from. I think there's going to be a debunk video coming though.
Now, Blue, can you just be a flat earther just for a minute? Okay?
Sure.
I don't know.
Blue, can you in your flatty mind, can you please tell me if you can bring back a ship with your P900, why can't you bring back the bloody sun?
I have never been able to answer that one either, Professor. Ever. And they act like nobody ever looked through a magnifying device at ships until the P900 came out.
Yeah.
Which is ridiculous.
Yeah, they had telescopes and binoculars back then.
Now look, who had the first telescope? Was that Galileo?
I think
pretty sure it was.
Yeah, Galileo. Yeah.
All right. So here's my story. When Galileo invented the telescope, the first thing he used it to look at was the bedroom window of the widow lady down the road.
Yeah.
The second thing he observed with it was the mast of a damn ship going over the horizon.
Exactly.
We've been using telescopes to look at this stuff forever.
Well, so
Maybe
you
there's-
couldn't answer that question.
Maybe that's another challenge you should put out the flirts then. Pick a particular spot on the Earth somewhere, say somewhere in the States. I don't know, wherever you want. 2 o'clock in the morning, just put the challenge. So at 2 a.m. in the morning, get a telescope and show us the sun. There you go. You should be able to on a flat Earth, surely, right?
Yeah,
How about,
that's what I'm
how
saying.
how about 15 minutes after sunset?
Just exactly.
Oh yeah, that'll do. That'll do.
Yeah. Just as soon as it gets dark, bring the sun back with the telescope.
How about 5 minutes after sunset? That's all. That's all you got to do.
Well,
5
it
minutes
doesn't. Yeah,
after
it doesn't
sunset,
really
bring it
give a
back.
damn. What I'm just trying to give like an extreme example. Say 2 a.m. You know, we just know it's going to be on the other side of the Earth somewhere, probably. You know,
of course.
Give or take, obviously depending on the time of the year. So I'm just trying to give us like a particular time. So at any time, they should be able to bring back the sun through their telescope, right?
Yeah, well, you'd expect to, because I mean, you can see the stars on the other on the other end of the dome. So
yeah,
why not?
Unless cool hard logic is correct, and the light just gets tired and quits.
Gives up.
Yep, just gives up.
It's a special photons.
Yeah,
They're like the moon photons.
But if you look at the size of their lit area of the Earth, the light's got to know it's got to quit at all kinds of different distances.
Oh yeah, that's right. Yeah, exactly.
How does it know how to do that?
I've got a feeling that the American flatties don't know that it's daylight somewhere else while it's night. They think it's nighttime all over the world.
Yeah, I think you do get some a bit like that.
Yeah, I know somebody who did a flat Earth model, and he kind of got the sun to start working, provided we have an inverse cubed law instead of an inverse square law for.
No, Stingray, isn't it?
Yeah, Stingray.
Mm-hmm.
Yeah, actually, it was I suggested that to him. Try a higher order Orloff ray. Yeah, and yeah, cubic kind of gets you a lot, or at least a lot closer. And then he invented some toroidal field effect from Gleam's suggestion that he doesn't know how the hell it actually makes the light rays bend, but bend they do, and that actually managed to give him sunrises and sunsets. But of course, unfortunately, it's not made with any physics we currently know or understand. Because
reasons.
That's the word I was looking for. Yeah, reasons.
Yeah. Oh, you got the spacewalk on. Didn't realise you had it on.
Aren't they fixing a magnetic spectrometer right about now?
Yes, that's exactly what they're doing, Professor. Yeah. I think
they're
coming to the end now. I think.
And weren't we talking about spectrometers a minute ago?
Yeah, it's a small world, isn't it?
There's a spanner floating around.
Yeah. Yeah, it's a bit funny because their tools are actually tethered to them, but they're also in a bag as well.
Yeah.
Yeah, we don't want them all flopping about, do you?
No, exactly. Yeah.
Yeah.
I think this is the last of. I think there's another one, maybe two more. I think after this of the spectrometer, and I think they've fixed it. It'll be done then. It's quite a few actually. Apparently, it's the biggest project in terms of the ISS on one single issue in its history, I believe.
Well, you know, there's
quite a few EVAs for this.
Yeah, I mean, this is sort of part of the particle physics that's
yeah,
that everybody's trying to get their head around, you know, from CERN, you know, so there's so much still to yeah.
I can't see the stars.
Don't start, Terry. And you could be quiet as well, Pip, saying things like that.
So the thing is that so what we're trying to look for in this is dark matter. And if you think about this, so if I asked you how big is the universe, and typically people would say infinite, right? Well, there's a school of thought that the universe is just expanding all the time, and space is expanding with it. And the reason that we know that is because dark matter is expanding with it. So therefore, dark matter occupies the space, if you like. And this is what the universe is expanding. So it's such a hard thing to get your head around, that space is expanding. Expanding into what is a good question.
But my question's actually not been all expanding to what, but mine's question has always been expanding from what.
Yeah,
what's the point that it's expanding from? Because that's how you imagine kind of like if you blow up a balloon, right?
Yeah.
It's expanding from the central sort of point. Yeah, they're all expanding. So where's expanding from? That's always been my question.
Well, let's just say that we got past that point where it's somewhere and then starts expanding. But where's it expanding to? That's the question. So in other words, it's how does it, if there's no space, how does it find space to expand into?
Yeah, exactly.
It's mind blowing.
My mind. Yeah,
I thought it was just creating new space in between the space we already had.
Well,
now my head hurts. Alan.
Yeah,
it's enough to hurt your head, I tell you, just thinking about it. So if the physicists who spend all their life still worry about that, imagine if you're a flurfer.
But I mean, it's hard enough to get flurfs to actually imagine the scale. Just the scale of our solar system.
Yeah.
And actually, the scale of the distance between us and the sun, is they can't get that.
Yeah, true.
It blows my mind. We get an echo from you, Professor.
You sure it's me? Because I don't even have YouTube up, I don't think.
I can hear myself when I talk. I don't think it's
Hello?
me.
Hello?
I can hear me too.
Hello?
Yeah, I was muted.
I'm going to turn my mic off just to see if it is me, and then you can tell me that, all right?
Okay.
I'm probably going to need help with this because I don't know what the hell I'm doing, as you know.
I think it's all right now. Yeah, it's all right now. I'm talking and not getting back.
Oh, what happened?
I don't know.
I don't know.
I have no idea.
I don't know.
Just had a spaz.
Oh, it was you, Alan, was it? Okay. I mean, it blows my mind, even just thinking about how far a light year is.
Yeah.
It's incredible. I mean, I don't know if I got my figures right, but one astronomical unit obviously is the distance between us and the sun.
That's right.
But then a light year, I think, is it 33,000 astronomical units, something like that? Is that right?
Just multiply it by up to seconds, and you'll have it. That's all.
I mean, that extraordinary distance. Then you're talking about billions of light years in the observable universe. I mean, that just blows my mind every time I think about that.
Yeah. Well, it's 150 million kilometers to the sun. Multiply that by so 150 kilometers, and then multiply that out to 2 years by distance, and they'll pretty much give it to you. But yes, it's phenomenal.
Yeah.
I know we won't be around when this happens, but you can imagine being on the Earth when you won't be able to see any stars in the night sky at all in another few million years.
Eventually, yeah. Oh no.
Yeah, I thought that was more like a few billion years rather than a few million years.
Oh, a few billion.
Yeah, billions of billions of years. Yeah. Well, by that time, our solar system probably would not exist after that.
I was going to say, wouldn't we though? I mean, wouldn't we though still be able to see our local galaxy, or will there eventually be a time when you won't even be able to see the local galaxy because of redshifting?
Well, we got a local galaxy is eventually going to merge with us, isn't it? They're going to come together at some point.
Yeah, no, but I mean the actual Milky Way, because I mean, we. Or is it just going to be that the Milky Way will be the last thing left that we will be able to see, and then even that will become redshifted beyond being able to be visible?
Well, you just think about it. It's a bit like that, like thinking about light, and it, I mean, we just happen to evolve because, to see light, because that's the major stuff that's coming from the sun. In that range. If the sun was producing something else, other than visible light, we'd have evolved to see that instead. So we'd be seeing infrared, or our bodies would be able to see radio waves.
Yeah.
I mean, there's actually there are, isn't it? It's bats that can recognize, because they blind to visible light, so they use use other electromagnetic waves to get around.
As far as I'm aware, bats do have some vision in the normal visible spectrum.
Do they?
But of course, they mostly fly at night.
Yeah.
And they haven't. And of course, they've got tiny little eyes, so they haven't got much in the way of an aperture. So they actually use sonar location.
Sonar, yeah.
Which is actually in for humans what we call the ultrasound range, in that it's mostly above what we can. I mean, young teenagers can kind of maybe hear it, which is a bit like those things they now set up to annoy teenagers and make them go away without affecting older people.
Yeah.
By playing
deaf as a doornail.
Unpleasant sounds above what most adults can hear, but at a level that is usually annoying to most teenagers.
Yeah, my daughter bought one of those today to show me, and she and I couldn't hear a bloody thing, but everything else could, like she.
Yeah, but other than but bats are using sonar, are using acoustic waves.
Yep.
As do, of course, cetaceans in the sea. I mean, they use acoustic waves to both echolocate fish when they're hunting, and of course for long-range communication.
Yeah.
Because those really low frequency sounds that the like the humpbacks and stuff make will travel a long way.
Yeah, exactly. Hello? Oh, you're still there. Good. I thought I'd lost you.
Yeah, we're still there.
We're thinking.
I'm trying to fucking around with this, and I've lost.
It was one of them points when I probably should have hit the
crickets.
The crickets.
Okay. All right. Okay. Let's see.
We got a video we can watch, Terry? Maybe.
No.
Yeah, that's what I just happened to be doing, Casual.
Casual.
What?
Great minds think alike. Catch a spaceman.
Well, I do have this Casual Spaceman video that says correction and apology. I was wrong.
Don't play any of that stuff.
Did use a fisheye lens.
No, don't play that because
not that Casual guy. God.
Don't play that.
Shut up. Nah. Shut up, Casual Spaceman. No. Don't play that. No, I'm serious. No, don't.
What else we got here?
Did somebody get something wrong? Did they?
Yeah, I got something
this
wrong.
Casual Spaceman did.
But that's the that's the difference between you and a Flurf.
I'll put it a vote. I'll put it as a vote to the peanut gallery in the panel.
What vote? What do you mean? Vote what?
So Casual, can I just say this? I always thought you were a larger man than me, but now I can honestly say that you're a big man. Because only a big man can admit to his mistakes.
Oh, thanks, Pete. That's the nicest thing any Australian has ever said to me.
Oh, see, I have got a heart, you see, unlike some of them.
If you want me to talk nice about you, Casual, you have to pay me £30.
And buy me some vape juice.
Vape juice, yeah.
Oh, bugger.
Casual, yeah, if you don't want me to play your video, you have to put money in the tin.
Money on
I don't want you to play the video.
That's right. So if you don't want him to, you have to put money in the tin.
Oh, have I got to put money in the tin as well then, have I?
Bloody play the thing then, I don't care.
Press play.
Oh, what have I done? I've broke something.
Terry, did you read that message in the side chat on the internal?
Yeah, didn't I reply?
No, it's all right. Oh, yeah. Oh, sorry. I missed that one. It's all right. Thank you.
I broke something. Now I'm trying to fix it.
Super glue, zip ties, and gaffer tape.
Yeah, I fixed it. No worries. Okay, we'll watch Casual Spaceman.
That's Where's Wally.
Where's Wally?
G'day everybody,
Much
Where's
better
Wally
idea.
here? Well, no fanfare thought he'd have a swipe at me, and I wasn't even going to bother with him because he's so inconsequential, but I thought it might have been a little bit of fun just to point out exactly where he went wrong. So, first of all, what you went wrong was not giving me a fun name. Now, look, Skew If, he's become insufferable around the office again because he's got the best and funnest nickname. Well, mine, I'm not even sure what mine is, but anyway.
Oh dear, guys. Give it up. It's not good telling lies, I tell you. Okay, so double W, where's Walter? He might try to tell you that the other two objects were satellites. So that's why the speeds are sort of matching. But Wade, he took some footage a bit further north, only about 100 miles further north, and he's got the footage of the supposed ISS. But he didn't catch another two satellites, you know. Anyway, they're going to come up with all sorts of excuses, but come on, guys. You know, you've caught two planes there looking roughly the same speed as the supposed ISS.
So, no fanfare. What you did wrong was you thought that because the light was moving, it was a moving light. Well, come on, guys. You can do better than that. Remember, Ruhif was tracking the ISS, which means any stationary lights would move across the frame. So if we look at this light, it's clearly a star. Because if you compare that to, let's say, where the ISS and a plane are, do you notice how planes have things called nav lights which flick on and off at regular intervals? Can't see that on either of these stars because they're stars. And you would have known if you had played a little bit more because, you were so full of cherry-picking nonsense you didn't bother looking at the rest of the video. And I even gave you a star chart, and you can see on the star chart, I'll put a big red arrow on it, look at that, there's a couple of stars right before it crossed past the moon. Could that have been what you saw scrolling past? Sure was.
There goes one. There goes two. And there goes three.
And no fanfare, did you even realise that I had the exact time stamped on the bottom of this frames as well? So you can see that when it passes those two stars, lines up with the star chart. Fancy that. So now you feel like a right goose. Why don't you just do the right thing? Ranty never does. He doesn't take down his videos when he's wrong, but maybe you can. We know you have before. Take your bat and ball and go home and delete your video, so maybe that's a good one to do that with, because you're really just embarrassing yourself here. Or maybe you can tell me where that 3-mile drop comes from the ISS, because at the moment, Harry hasn't. It seems like he's just extracted that number from somewhere the sun doesn't shine to me. I mean, where the ISS is orbiting is what I meant. Anyway, no fanfare. Well, That was nice, but try and think of a nicer nickname for me, will you? Something that's a little bit funny, something that gets me a bit of kudos around the office. So, fresh look on truth and no fanfare. I've given you all the facts and figures, and all you've given me, Harry, is words. And by your own words, Harry, you don't accept words, so I guess you two are going to have to come up with some facts and figures. But to that end, you guys are actually very well placed. You're a bit like Ruhif and Wade. So Harry in Sydney and no fanfare halfway up the coast, you should be easily able to find an ISS track that goes straight over both of you. If you'd like a hand with that, I'll leave you a couple of links in the description, and if you want, get in touch with me. I'll tell you just how to go about doing it. And then you'll be able to refute it because you'll actually have some data.
Ooh, geez, you make yourself look all clever there, where's Wally? Eh?
You know, that thing that we all like to see is data, not just words. I actually agree with Harry on that. Words, cheap. Data, that's where it's at. So let's see it, guys. I look forward to it. So, Wolfie, I've got your approval to do this NFF slap, yeah?
Okay.
Yeah, look, I know we said we're ignoring him.
Yeah.
Yeah, but he's being a real idiot.
Got it.
Look, it's too easy. He just said some stupid stuff about stars being planes.
Sounds good to me.
Oh, yeah, I knew that would get you. Thanks, mate.
Go for it, mate.
Yeah, I know. He's made 2 videos in a week trying to get your attention, but yeah, we'll just ignore him after this.
Okay.
So, Wolfie, for those of us who came in late, what do you think's got NFF's knickers all in a bunch?
Yeah, okay. Just to give you a bit of background, I went to the guy's channel once over 3 years ago when I was doing some research for a P900, and he had a couple of videos shooting whales with his. I immediately recognised the area where he was shooting from because I'm familiar with the New South Wales coast quite well. And I just made a friendly comment about whether he could see Ball's Pyramid or not. And the guy just lost it. He just went nuts. So I gave him a bit of stick back, and then he was crying about it for months. I actually even apologised to him. He just can't let go. The poor sod. I picked him as a stalker on day one, and I've been proven right.
Oh, NFF. Man, I have never seen a guy who simultaneously wants something from you and is so prepared to insult you to your face. My goodness, I haven't even provided you the links yet, and you're already back into me, mate. Just as well what you say to me doesn't really matter at all, eh?
You're helping. You're helping me. Good, darling. That's good, darling. You're a good helper. Yeah, that's it. Okay, a little bit more. A little bit more. A little bit more. A little bit more. We've closed this power.
Looks like fun.
It is.
Yeah, I was going to say they really look like they were enjoying themselves, didn't they? Mind you, who wouldn't up in a light aircraft? I love flying.
Can I become
Just
a
can't
pilot
afford it.
instructor?
Hmm?
Can I become a pilot instructor?
Yeah. Possible.
No.
I don't know how likely it is, but yeah, it's possible.
It's highly unlikely, Blue. I don't have the time or the money.
Yeah, because there have been claims that I have never actually proven that I'm the one flying the aeroplane, and that's fine. I just want to show you the real proof that I'm actually the one in the pilot seat making the video. I'm just going to pan around in this room. I'm in a hotel room, and there's absolutely nobody else here. Okay, just panning around. I'm the only person in this room. Now, I'm going to show you my left wrist. And you can see there's a discoloration there. That's from an injury I received many, many years ago, and the colour in the skin just went to this light colour, and it's never basically healed. But anyway, that's a distinct feature on my body that you can use to identify that I'm actually flying the plane in the following clips. So I'm in the cockpit just prior to a departure today, and there's the discoloration on my left wrist. And those are the stripes on my uniform, and I'll get some more video from in flight.
Oh, look, he's flying.
he's actually flying. Wolfie's just telling him how.
Yeah.
Yeah, well, that's isn't that the nice thing about modern aircraft? Although I suppose to some degree it's also not such a nice thing about modern aircraft.
Yes, it's Wolfie, and yes, I am flying the airplane. It's a real airplane, and yes, I'm in the pilot seat.
CGI.
I was going to say they will practically run an autopilot from takeoff roll to the end of the landing line.
No, it's the newest flight simulator from Microsoft.
And there's the discoloration on my left wrist.
I'd just say it looks so real nowadays, with technology.
I don't know that thing will do a Category 3 approach, but it might. I don't know.
I think that's practically everything that you get in.
And it's the 16th of August.
Any commercial airliner.
So Blue, just for people like myself that's uninitiated, a Category 3 approach, so obviously it winds itself up.
Yeah, Category 3, the airplane.
So we just crossed the equator, which means
okay, so that's landing gear and everything, yeah?
Yep, it can do the entire landing sequence, yes. But that takes a special aircraft and a special crew.
Okay, it's all good now.
While we're on planes, let's listen to an expert on head-up displays, shall we?
Yeah. So, 16020, your plane flies at 3 degrees. Okay? At
It
3
does.
degrees.
Absolutely.
Your your HDU is set horizontal, and then you fly at 3 degrees. Lo and behold, looks like the horizon has. Do you see? You freaking idiot!
Oh, sorry, I meant self-confessed expert. The Dunning-Kruger
I
is
can't
strong with
believe
fatties.
how
Let's
with
listen
such
to an
confidence
expert
these people
talk
can
about
say
Dunning-Kruger.
stupid.
Fractured escape. Dunning-Kruger has two learning curve. When you come out of the indoctrination centers, you're stuck on MT. Stupid. MT? Stupid? MT. I'm not sure what you mean by MT.
Oh, sorry, yet again, that's a self-confessed expert. It's just so perfect, though, when he tries to talk about Dunning-Kruger, and someone in the comments made a comment about Mount Stupid, that Pookie just read it as MT Stupid and didn't know what the heck he was talking about. Because everyone knows the very first thing you learn about when you're talking about Dunning-Kruger is Mount Stupid. Upper left, that's where these guys are sitting, right on top of Mount Stupid. Okay, so if you like that, how about you click and share and subscribe and be the first to get in on the next fun little adventure into destroying the flat earth.
Well, this idiot's going to burn the hair off his arm. Watch this. This is funny.
Don't try this at home, kiddies.
I'm an idiot. I'm an idiot. Alan! Ow! Alan! Ow! Steve!
Why am I thinking about ants and magnifying glasses at the moment?
That's nearly as bad as the conversation I was having with Rich the Black last night about oxygen systems in aircraft and the fact that the airlines are now allowing pilots to wear beards, and them using products that contain mineral oils on the beard, with what might happen if you then have to put a mask on that's pushing out pure oxygen.
Yes.
Because apparently you can get the O2 concentration up high enough to spontaneously combust the beard.
I was about to say, why am I thinking about a diesel engine at the moment?
Exactly.
Nice house.
That's actually not a house. That's the headquarters of the British National Rifle Association at Disley. That was built in the 1890s, and
That's not
is
very
typical.
old for these guys.
No, but it's built. The whole camp is actually built in British, what you would call British colonial. A lot of the clubhouses are actually.
I think it finally feels like a Final Days date.
Applied by. by the same company that shipped an awful lot of the pre-packed buildings out to many of the colonies, especially Australia and New Zealand.
Yeah.
Oh, logic.
Yeah, we've got this. We'll
Who's-
make this the last one because we'll be
Who's
going
this?
for we'll be going for nearly 6 hours when I finish this. This is Logic.
This is Logic.
Logic. He's one of the old school debunkers. He's been around for quite a while.
It's part 1 too.
Today. Now, I know there's not a lot of lower fruit than this, although that kind of applies to everyone I've responded to this year. I do think, though, that of all the channels I've looked at, this one's among the more important to talk about, because believe it or not, there apparently are quite a few people who buy into this. This channel has 25,000 subscribers and regularly gets about 150% of that in views, meaning 30-some thousand. It seems that the number of people who are so unfamiliar with the basic functionality of cameras and digital images, and who are so obsessed with the Bible to the point that seeing perfectly ordinary images throws them into a panic about the end of the world is kind of amazing. If there was ever a decent argument for photography classes in schools, I guess this would be it. Much more importantly though, I still consistently get a bigger laugh out of this channel than any other channel, so I just want to. I hope you're in the mood for some lens flares. If you're not, just leave me thousands of profane negative comments.
Call centers were actually hired to leave thousands of profane negative comments in order to discredit the channel, thanks to your tax dollars.
So what are we looking at today?
Today we will be viewing striped and heavily cratered celestial objects rolling across the sky, and several other sky and space anomalies not mentioned in mainstream news.
Well, that's unexpected. What a nice change of pace. Seriously though, I'll try to cut out anything I've looked at before that I don't have anything new to say about or that isn't kind of different. Or I'll keep it in if I think it's fun. Whatever. But don't worry, I'm not just going to be talking about old stuff. I picked this particular video because it has some interesting extras. Oh, and for anyone who hasn't seen the first two videos, the fake sun and the looming lens flare planets and the fake sun and the airport Yeti, you do well to go look at those first because I reproduced a lot of these effects in those videos and I'm not going to repeat those demos here. If necessary, I might put in clips of the original demos, I don't know. But even beyond those demos, some of what I'm going to say here will assume that you've seen those other videos because I don't want to be spending all my time repeating myself. So I'll link to those in the description.
The purpose of this channel is to show the viewers that we are living in the very last days according to the Holy Bible, and to explain why this is very good news and cause for celebration.
I've always kind of wondered which direction your reasoning went on that. Did you just randomly find yourself looking at FAA weather cams one day and you started seeing a bunch of lens flares and glare and dust specks and black spots on sensors and so on, and you just couldn't think of how to explain it, and so you started trying to figure out some grand unified theory of dust specks and decided the best fitting explanation had to be that the vague predictions of signs in the sky from the Bible are coming true? Or did you start off a hardcore Bible believer thinking you must be living in the end times, please God let me be living in the end times, unlike all those people through the past 2,000 years who thought the exact same thing you think, and so you started hunting around for signs in the sky in crappy weathercam digital photos, instead of in the actual sky for some reason, all in the desperate hope of finding anything you could interpret as a sign. Critical thinking be damned. I'm guessing it was one of those, and I have my guess as to which one it was, and I bet pretty heavily I'm right. But I'd actually love to ask you directly. A live stream, or even just a private chat just to ask some questions would be pretty great. There's a lot of things I'm curious about regarding this vast global fake sun conspiracy version of Christianity that so many of the videos I've replied to this year are based on. But unfortunately, you seem to make yourself pretty hard to contact. There's no private messages on YouTube anymore, you have comments turned off, so I don't really see a way to ask you my questions directly. Oh well.
Many of you have seen this celestial object, which is orbiting Earth, hundreds of times from many different cameras in Alaska and Canada.
And sometimes in a bunch of weather cams at once, putting it at totally different locations. What an incredible celestial object.
The reason we are starting out with this footage is to remind viewers of some fundamental rules of lens flares.
Can we start with the fundamental rules of real planets?
1. A lens flare of the sun doesn't rotate.
Right. At least if you mean rotating on an axis like a planet, yeah, right. And since there's no sign of it rotating, it's consistent with the lens flare so far. Sure, the sky's changing color under it, clouds are moving by behind it, there are plenty of compression artifacts coming and going essentially at random, but there's no sign of any repeating pattern that would hint that this is a rotating sphere.
A lens flare of the sun is a small reflection of the sun, which rotates only once every 27 Earth days.
Doesn't matter if it rotates at all. The sun is way too bright, and the quality of these images is way too poor to see detail on the sun like you would through a solar filter.
2. Lens flares of the sun do not have craters.
I agree, and given that there's absolutely no sign of craters, it's still consistent with a lens flare. You remember when I said there are no repeating patterns that'd hint it's a rotating sphere? Well, that's true, but there are some repeating patterns. The coarse DCT basis patterns that comprise each square, because this is a JPEG image compressed to a ludicrous degree, probably to save bandwidth and storage costs. You'll notice that these patterns, which are what you're mistaking for craters, continue all across the image. They're not confined to the lens flare. And you'll also notice, if you look carefully, there is no planet-wide repeating pattern of those square patterns relative to each other. If these are really craters on a planet that's spinning, you should be seeing the same craters in the same spots over and over and over. But you're not, because this is just compression. All you're seeing is a bunch of squares that represent as well as possible whatever happens to be in that bit of the image in the current frame, so the pattern in each spot is going to constantly change, for all intents and purposes at random.
3. Sun lens flares can never go behind clouds or other objects in a photo or video.
If you saw something that looked like a lens flare, but it was being clearly and unambiguously eclipsed by something in the sky, then yeah, you would have to reconsider what you're looking at. But there's no sign of that here. The visibility of parts of the lens flare is affected by the changing color and brightness of the background underneath it, or by the original light source, the sun, being obscured, which might make the flare look like it's partially obscured even if there are no clouds in sight. But there's no indication here that a cloud is getting between us and the lens flare. Be careful not to misinterpret what you're looking at just because you want to. Advice I'm sure won't be followed, since your goal seems to be to misinterpret everything you see as much as possible.
4. Lens flares of the sun can never react to sunlight in a video. For example, a lens flare cannot become partially illuminated by the object causing the lens flare.
Meaning, for example, that you wouldn't see half of it lit by sunlight and half of it in shadow like the moon? I agree, so we have yet another way this is perfectly consistent with a lens flare. You see how the sky has a color gradient? Well, that's showing clearly through the lens flare. The apparent brightness of different parts of the lens flare always conform to the background color of the sky, and it never looks lit from the side or silhouetted from the back, even though if it's really in the sky, the sun would be behind and beside it throughout this video.
Please remember these elementary facts as we go through these FAA videos.
I'll be sure to do that, thank you. I didn't expect you to lay out half my case for me, but yeah, thanks.
NASA's equipment is much, much closer to the Earth than the Sun. This is why the sun often appears to cast two different reflections in the water, such as seen on the east-facing camera at Taku Inlet, Alaska.
Oh, I see. Wait, if the sun simulator's close, it casts two reflections. Why? Why does not being a real sun make something cast two reflections? Or are you trying to say something like the real sun's at a totally different point above the horizon and we just can't see it? In which case, if it's casting that much light, why wouldn't we see it? I'm not following your reasoning here, if you have any. Anyway, as usual, you've mistaken a property of an object that reflects light, in this case the surface of some water instead of the inside of a camera lens, for a property of the object that produced the light. For some reason, you think an explanation like, there are two suns, one of which is not visible, but produces a reflection, like a reverse vampire, is a simpler explanation than the water's a little bit more or less ripply in different places. And I say ripply because here's what's actually happening. In more rippled sections of water, the sun glitters more off the tops of the little waves. That's what you see happening in the distance right in front of the mountains. The light from the sun, that if this were a perfectly flat mirror-like surface would just reflect away at the wrong angle for us to see it, instead reflects off at odd angles from the little waves, which obviously have surfaces at all different angles, and in some places reaches the camera. In the smoother areas, though, the water acts more like a flat mirror. If you look carefully at the water, you can easily see that there's a difference in the surface texture of the water in different areas. Really close to us and really far away from us, the water looks more light gray, but in the middle, where that glitter path disappears, the water looks almost black. Not so much here, where what you have to reflect are more distant, lighter-looking mountains and the sky, but certainly to either side of that. And that's because, where it's a little bit wavier, you're getting reflections off those odd angles on the surface from all over the place. And most of all over the place is the sky, which is pretty light. but in the smoother sections, it's much more effectively reflecting those silhouetted, almost black-looking mountains. Here's a really similar effect, but with a bit more variety in what's being reflected. Notice how the smoother surface reflects the buildings really well, making the water, where they're reflected, a lot darker than in the rippled areas. But between the buildings, it's reflecting the sky a lot better, making it look brighter than the ripply areas. If those mountains weren't there in our picture and it was just sky, that's what we'd be seeing in those smoother sections of water. And like I said, that's why that area just to the left of the glitter path looks so bright compared to the rest of the smooth water. There's a gap there between the really dark looking mountains. Closer to our camera where the glitter path comes back, the narrow part is just the same effect of rippled water that we saw before, but you see that towards the very, very bottom, it starts widening out a lot more. And that's because if you could tilt the camera down, you'd see that that's where the real reflection of the sun is. If the water was all a flat mirror, that's where the correct location of the sun would be. And I can sort of show you that by roughly cutting out the reflections of the mountains, which is a little bit tricky since the reflection of their tops on the right side is a little bit messed up by the ripply water. So when I say cutting it out roughly, I mean roughly. Then I'll mess with the colors a little bit to make them more visible, flip it vertically, and reduce the opacity so you can see the original mountains with the reflected mountains on top. And now you'll notice that that wide bottom area of the glitter path is approaching where the actual sun in the middle of all that glare should be. And in the preceding frames you showed us, we can actually see the reflection of the sun, of course with some glare around it, moving down into that position as the sun rises. This stuff, looking for the glitter path, looking for interruptions in it, stuff like that, is common knowledge that's been used since the distant past to determine the conditions on the surface of water. This is nothing new, but somehow despite its incredibly long history, it comes as a surprise to you. I honestly don't get how you manage to pay that little attention to the world around you.
This equipment is capable of producing a circular glare, thousands of miles in diameter.
Wow, what a coinkydink. Cameras at high exposure are capable of making that exact same kind of glare. That's so weird. We've been over all that before, though. We can do something more interesting.
However, whenever it passes behind a narrow object, such as this thin flagpole, it completely disappears. Our real sun could never disappear behind a thin flagpole.
You serious right now, dude? You're gonna make me do the light pole all over again with a flagpole? What is it with you and poles? Well, okay, here we go. So obviously we all know that whether anything can be hidden behind something else depends on the apparent size of both of the objects, which is a function of both real size and distance. By which I mean if there's a pencil 100 meters away, it's hardly going to block out anything you're seeing, but if you hold it right in front of your eyeball, it'll block out pretty much anything. This is what you might like to call a
fundamental rule.
And it's not one you disagree with, even if you might think so. It's one you recognize and operate based on every single day. It'd be pretty hard, for example, to walk or drive your car if you didn't intuitively comprehend it. So it should go without saying, and yet you consistently forget it whenever any type of pole enters the frame of a picture. Having said that, though, of course that doesn't debunk what you're saying. So is the flagpole actually close enough to hide the sun, or is it not, and therefore you might have a point? Well, from the airport code, CYDB, we can find out that this is the Burwash Airport in the Yukon. We don't need to know anything else to do this the easy way. All we need to do is compare this image of the west-facing weather cam with the reference image helpfully provided by Nav Canada, because the reference image helpfully tells us what angles we're looking at. Now, the camera's been turned slightly since the reference image was taken, but the field of view is still the same and the flagpole looks about the same size, so it doesn't matter. We'll overlay the reference image on your image and then duplicate the flagpole a whole bunch of times to find out how wide it is. This 30-degree section is about 36 flagpoles wide, making the pole just under a degree wide in the image. If the sun's angular size is 30 arc minutes, or half a degree, then just from this we can tell that the flagpole is plenty wide enough to hide the sun. And that's without even taking into consideration the fact that the pole gets wider the lower you go, and that the folded up blue tip of the Yukon flag means that it's not just the width of the flagpole that can hide the sun here, but actually more like double that width. So that's the easy way to figure out that the flagpole is plenty wide enough to hide the sun, and I'd be entirely right to call it done and move on now. But you gotta remember, this is logic, and this is a pole. We don't do poles the easy way. So let's do it the hard way and double check our work. Here's every useful picture I found of the terminal building at Burwash Airport so we can figure out what we're really looking at. This one is the most interesting, I would say, because we can actually see the weather cam. It's not too relevant right now, but at least I'll know the kind of thing to look for if I ever need to know about Canadian weather cams for some reason. Now from this we can see that the thing in the upper left corner is the corner of the roof. To get an idea of the width of a typical flagpole, the flag store has flagpoles that vary from a constant 2 3/8 inch wide to a tapered pole that goes from 3 inches at the base to 1.75 inches at the top. These are 20 to 25 foot poles, which is a very normal height, and it also looks about right. The telescoping pole is more like what we're looking at. You can actually see the rings or joints or whatever you call those. I'm not up on my telescoping pole terminology, sorry. So let's call the width somewhere between the width at the top and the width at the bottom, say 2.5 inches where it covers the sun. Here are some images with the flagpole and the building in the same picture so we can get a general idea of how far away the pole is from the camera. Now, the typical Canadian flag you would fly on one of these poles is 6 feet long, and I think it's very generous to guess from this that the flag is at most 20 feet away from the camera. Personally, I'd say that's way too high of an estimate, which is good because I want to give you as much of an advantage as I can. If you think it's too low of an estimate, I don't know what to tell you. Find a way to measure precisely and put it in the comments, I guess. Prove me wrong, same as usual. Now all we gotta do is punch those rough numbers into our angular size calculator, and remember, the sun, not the glare that you see in the camera when you look at it, but the angular size of the sun itself, which you can easily see through a solar filter you can get for like $10 on Amazon, you have no excuse, is about half a degree. So an object 20 feet or 240 inches away and 2.5 inches wide will subtend about 0.6 degrees. So just on its own, that would be just big enough to hide the sun. And when we include the width of the flag that about doubles that size, it's even more comfortable. If I were to guess just from looking at the picture, seeing where the center of the still visible glare seems to be, I would say the sun probably isn't just behind the flagpole. It's probably partly hidden by the pole and partly by the flag. You can see quite a lot of light coming through the much less opaque single layer of white, and you can see just how much light gets cut out just by folding that white part over on itself once. It's pretty significant, and the blue part, being darker and folded over a couple times like it is considerably more opaque than that. So there you go, that's the hard way, and I have to say it wasn't anywhere near as hard as the Drumheller light pole. I'm a little disappointed. Wait, whoa! Why is the sun making multiple reflections?
To find out where the real sun went, please watch our March 23rd video.
But I already know where it went. Oh, whatever, let's do it. I'm in a poly mood. I want to stay on your pole all day.
The reason this is happening is because the light source we are viewing is the glare produced by the black dot equipment that reflects upon the water surface.
A lot of what you're seeing is glare, I'll give you that. The unavoidable fact of glare is why it's a really good idea to use a solar filter if you want to see the real size of the sun, and why it's so unbelievably stupid that you constantly say the sun is giant when you see a bunch of glare. Of course, the point of these weather cams is not to measure the angular size of the sun, that's not their purpose, so nobody really cares what the sun looks like. Unfortunately, that lack of caring, and thus lack of implementation of solutions for glare, has the side effect of leading unbelievably incompetent image analysts to proclaim that the sun must be fake because they confuse glare with the sun itself.
Where's the real sun?
Behind the pole and the flag, just where you'd expect.
It is currently behind a dark nebula that we will be looking at in just a minute.
No, we won't. We're going to finish the flagpole, then end the video.
To refresh your memory on the approximate size of the
Dark
real
nebula.
sun, here is an inset of the real sun we just saw moments ago in Portage Glacier. The real sun could never be hidden behind a thin flagpole.
Oh, so is that why it's in front of the flagpole then? I mean, if we're denying that glare exists in this picture and saying the entire thing here is the real sun, then apparently the sun is between us and the flagpole, right? That's not just glare coming around the edges, that's the sun. Is that what you think? Are you sure you've thought this through to the end? Alright, well, we've got plenty more stuff to look at and some very interesting revelations about the Final Days' previous YouTube channel, Universal News Media, which is the one I first responded to, and why that channel ended. But I'm going to leave that stuff for the next part because this is a really good point to pause before that starts. I want to give a massive thanks to all the supporters of this channel on Patreon, Subscribestar, PayPal, Paywhirl, any other method, you're the best. If you like the video, give it a like. If you don't know how cameras work, give it a dislike. Subscribe if you want to catch part 2. Sign up to my email list at list.logic.com for early access. Join my Discord, and don't forget to feed your cat. See you in part 2.
Very good.
Yeah, Logic rocks.
Yeah, I like them.
Yeah. Good old Logic.
Yep.
Terry, there's a message for you in the internal chat. Terry.
I think Terry nipped out.
No, I'm here. The microphone must have been off.
The video can't pause without Terry.
Yeah, I was going to say, yeah.
Yeah, the video can't pause without me.
Yeah.
What he said. Have we got it? Have we got time?
What, Simon Dan's video? Of course we've got time.
Have I got time?
Always got time for Simon Dan.
Yeah, but I haven't. I have to check to see if I've got him on the bot. No, the bot hasn't picked him up yet.
Did he just drop it?
Look what I've got happening at 4 o'clock on Wednesday evening. Sorry, 4:45 on Wednesday evening.
Oh.
Okay.
6 miles from home.
Oh.
They get the wheelchair oiled up.
I can get the bus there. It'll be dark. I don't know. I can get the bus home from there as well.
And knowing
16:42. It'll be dark enough, yeah.
Knowing you're like Alan, you'll get it on your
it's-
first go.
It's a quarter of an hour after sunset.
Yeah, that should be good.
It's a 1 second pass.
Yep, that's good.
And the other thing is, Rosie lives within about 300 meters of the centre line of it too, so I could go to hers too.
Oh, look at that!
Perfect.
And then
It
she
just
can
misses me.
Want to see some good video then, Terry, Alan?
Yeah, well, I guess I'm going to have to borrow Nathan's 550D and screw that on the back of my.
Castles, you try it because it goes over Ireland. It's just out of my range.
Is it? Oh, I'll have a look later.
Yeah, hang on, I'll zoom it out and you can see where it goes.
I haven't got a decent camera to capture it though.
This is a different one, Alan.
No,
It's another one
yeah,
else.
it's a different one. The one that goes the other way is next Saturday, I think, if it hasn't moved much. This one has moved a bit.
You're not going to get
This one's moved a couple of kilometres in the last week. The centre line's moved.
The other one is
northwest a
going
couple
kind of
kilometres.
yeah. The other one's kind of northwest to southeast.
My last 3 good ones, Alan, have been nothing but cloud.
Yeah, that's the problem. I'm looking at the weather forecast on AccuWeather for Wednesday, and it's talking 70% to 95% cloud, depending on if they class it as afternoon or evening. Yeah, it's sort of like it's the picture of the moon with the cloud in front of it.
Mm-hmm.
Yeah, and no ISS transit. Yeah, I doubt you'll catch it, but you try. No harm in trying. You never know. You might get a, gap between the clouds if there is clouds.
Send up a GoPro on a balloon.
I've going to say, at least it's a nice phase for photographing the moon anyway, isn't it?
Yeah, it is. Got to run, guys. I'll see you later.
Oh, okay, Blue. Thanks
Bye,
for
Blue.
dropping in, mate.
Take it easy.
Bye, Blue.
Oh well, I'll just watch Simon Dan on my own then.
That's all right. There we go.
We just watched the debunk video of Simon Dan's video.
What?
Where is it?
Yes.
What did I do?
Simon Dan's latest video is about something about a $200,000 challenge or something.
Yeah, and we've watched the one that they debunk him, apparently. So they think.
Oh, okay. Oh.
So we're watching him back to front.
No, not to. Doesn't matter. Don't worry about it. I didn't know you'd already done that, so not to worry.
Yeah, we're just all trying to figure out how to get.
Other one,
we're just trying to figure out how to get water to stick to a ball.
Cash will take 3 Valium and have a sleep.
No, I was thinking of finishing up now. We've been going for 6 hours.
That's in the stairs, yes.
Yeah, that's a bit too far north for me. See where see where the lock in the middle of Northern Ireland is.
Yeah.
I'm just slightly south of that.
Okay. Let me see.
Move.
What's your latitude? I'll stick it in for easier.
My latitude, I haven't got a clue.
Yeah. I'm 55, so you're probably what? Say 52, something like that.
Hold on, I'll look it up. Hold on.
It's closer to 55 than 52 because I'm 52 here in Norfolk. In fact, I'm 52.7.
Oh, right, okay.
I'm 54.4.
Right, I'll stop 54, right?
Yeah.
Oh, I don't. What is
In about half an hour or so, I'll know what my latitude will be because I'll be in bed.
54.4 north, 6.4 west.
It's just not let me put in a longitude. Okay. I'll just go in my longitude. 54. And 27th.
Oh, that's a bummer.
30th.
So, who's out in the peanut gallery? Irish Stew, Wolfgang, Dora.
Irish Stew never goes. He's always here.
None closer.
Dora, Adam L. Kristen's already gone. Now, if Sir comes back in again and says, I didn't say good night, well,
good night, everybody. I'm leaving.
Yeah, we all are. We're all leaving.
Night, Professor Phil.
Bye,
Good night,
Phil.
Phil.
Yeah.
Good night, Phil.
Have a great evening. And,
You too.
Wolfgang was in.
Great
Sorry,
conversation.
Wolfgang, we're leaving.
Thanks for that stuff, Alan. It was really good.
We haven't
Thank
finished with
you.
the sun yet, Phil, so next time we're
Okay.
on.
All right. No worries. Catch you later.
Later then.
Bye.
Bye.
Still haven't finished with the sun. Wow.
Bye. Bye, Pete.
Demonor says Rajko now knows your location for his cannon.
Real sock on sec, what was there? Brainery. Jeez, I don't want to go too
Wolfgang,
far.
hello, cheerio.
I'll go too far. I'll end up going too far up the list. Demon Orb. Yeah, we're all going now, saying good night.
Right,
Bye,
good night,
everybody.
everyone. Good night, everyone. Bye. Good afternoon or good wherever you
Enjoy
are.
your haggis tonight, everyone.
Yeah.
You got anything for us, Alan, before we go?
No. I could try saying it's a rare brick Munich nicht.
Well, you could try. We're not very good at it, are you?